there. There's on this sort of tutorials on the weighted constraint satisfaction problem and how we can solve it and try to connect automated reasoning with machine learning and deep learning. So this is a joint work with joint presentation with Simon de Givry, but we got some support from George Katsirelos, Nathalie Rousse, and Céline Brouard. I want to thank them here. So the preliminaries, just to give you a quick idea of what we will do a mix of basic and advanced theory and algorithm, trying to show connection between fields. So I will talk a lot about LP, for example, but also QP, and also a bit of Markov random field, and a bit of CP and COP. So a bit of everything, actually. We will try to have some practicals on a virtual machine with Toolbar 2 and more, Minizinc and Soplex installed on it. The idea is to make you curious and dig. Even in 3.5 hours, it will be difficult to present everything. And this, I hope you will enjoy, whether you like theory, whether you like algorithm, or even if you like coding. And the presentation will be essentially in 4 parts. The first part will introduce the cost function network framework, and we will be coding together a visual Sudoku solver using PyTorch plus Toolbar 2. The PyTorch work will already have been done, and Thias will cover this better tomorrow morning, I think. Then we will dig into algorithm and theory and show how it works. It will not be exhaustive. We have to make choice because there's too many things to present. Then Simon will come in and he will show you how you can really use Toolbar 2 to model and solve non-naive problems like airline scheduling problems or block modeling problems, among others. And then I will come back and maybe Simon will do something also and show how we can connect cost function network with machine learning algorithm, and actually how we can learn the Sudoku rules or how to play the Sudoku without ever coding the rules of the Sudoku. So we have to learn them from data, from images also if needed. So yeah, I saw that many people downloaded the VM, so I hope you downloaded it. It's big, I'm sorry, we try to make it as small as possible, but there is plenty of stuff in it. And so you probably did this stuff. If you didn't, it's not so risky because, okay, I will try to run the VM on this new machine. I had to change machine because my laptop was apparently not able to run this webinar version of Zoom. I don't know why. So it's a new machine. The VM has been quickly installed on it. I hope it will work. So yeah, where all this started? Where do these cost function network come from? Essentially, originally what Simon and I have been doing for most of our time during his thesis and during my work as a young researcher was constraint satisfaction, constraint network, and constraint programming. And I'm very happy that Pierre Schaus did this quick tutorial yesterday because you should know more or less what I mean by constraint network. So you have a sequence of discrete domain variables, so a set V. Bold letter will always be set or sequences. Then you have a set phi of constraints. And in my case, I will be a bit non-standard. Usually people present constraints as relations, set of combinations of values that are authorized or forbidden. In my case, I will prefer, and you will understand why later, I will prefer to define a constraint as a Boolean function. It's simply a function which takes the value of the variable which are involved in the constraints, in the scope of the constraint, and it returns a Boolean, either true or false. Whether the tuple is authorized, in this case it says true, it's okay. And if the tuple is forbidden, it will say false, it's not okay. And so we have all these small Boolean functions which are constraints. And then if you want to imagine, without even asking yourself a question about what you want to do with this subject, you may ask yourself, what does it represent? And actually a constraint network just represents what we call a joint truth function. So you take all those small functions, the phi s, which come from your set of function phi here, and you combine them with a logical AND. So as soon as one of these functions is false, the output function will be false. It's only if they are all true that the join function will be true. And this is it. What is the meaning of a constraint network? It's just a Boolean function, a joint huge Boolean function. And on this function, you may ask yourself some questions. And the most usual one, of course, is this famous constraint satisfaction problem. It's NP complete. And the typical question is it possible to find a value for all variables such that all constraints are simultaneously satisfied? I can rewrite it in terms of the join function as, is it possible to make this join truth value function true? It's exactly the same question. Or even if I order my two elements, if I consider that true here is always less than false, then my question could be an optimization query. Actually, it could be, okay, but what is the minimum of this function? If the minimum is true, then we know that the problem is consistent. If the minimum is false, we know that the problem has no solution. And that's where we started. And this kind of framework can be used with different languages. So a function can be described in various ways, and this has an influence in terms of computational complexity and implementations, of course. The most basic framework is using propositional logic with conjunctive normal form or clauses to express constraints. So you have an example here. What is a clause? Imagine you have Boolean variable only. You can define the negation of a variable, and a clause is just the disjunction of either a variable or its negation. So this is an example of a clause. Actually, a clause gives a really tiny and atomic level of information. It says that just one tuple is forbidden, because to make this clause false, it's a small function, and to make it false, there is only one assignment that makes it false. Otherwise, it's always satisfied. And this is a very simple way. The note which I want to make at this point, and if you use Boolean variable plus clauses, of course, you are using SAT. And the interesting stuff is that this language is not closed under negation. If you take the negation of a clause, you get something different. You go to the disjunctive normal form. And so this language is sensitive to negation. What we do when we deal with a constraint network is we use tables, Boolean tables, to define the functions. It is now fashionable to call those tables, when they are multidimensional, tensors. So a tensor is just a table with more than 1-2 dimensions. If you have 3 dimensions or 4 dimensions, so essentially if you have 3 or 4 variables in the scope of your constraints, then you will need tensors. But let's stick with tables, it's more simpler for us. Here, I give an example of the Boolean matrix, in this case, which defines the equality constraint. Effectively, if you imagine I have 3 values for the first variable here and 3 values for the second variable here, if I choose the same value for the 2 variables, I end up in the diagonal of the matrix, and I know that my equality constraint is true, and I have a true on the diagonal of the matrix. If instead I take the value 2, for example, here, and the value 1 here, I end up having a function which is equal to false because 1 is not equal to 2. So this kind of simple Boolean matrix suffices. It's the same as a relation. It defines a relation, actually. It's just more dense. We have all the information, but it suffices to represent constraint networks. The nice property compared to clauses is that this is insensitive to negation. If I want to shift from pairwise equality to pairwise difference, the only thing I have to do is to change all those true to false and all those false to true. And the matrix will define a Boolean function which corresponds to difference. And we will see this more in detail in the practicals for our cost function network. And the last type of language that you can use, and I think that Pierre Schaus yesterday gave many examples of this with the sum constraints and, for example, the all different constraints. So this is this one, is using a specialized language. So you can forget about clauses, you can forget about tables, you could use a specialized language in which you can express specialized constraints such as the sum constraints or the all different constraints. And this is the third level. In this tutorial, we will not use the global cost functions inside toolbar 2, but there are some of them, but we will not use them. We will keep the simplest level of tables and tensors. And as you know, and as Pierre probably presented yesterday, you know that CP, SAT, and constraint, well, CSP, CP, and constraint programming and SAT are quite useful in practice. They can solve digital circuit verification problem. CP is good at scheduling and also at resource management in general. SAT has been extended to solve harder problems like planning or software verification. Also CP there, and theorem proving with the recent proof of several theorems actually, but the most famous being the Pythagorean triple theorem with the 200 terabyte proofs. So they are very successful, these items. They excel at the analysis of complex and perfectly known systems. But Simon and I work at INRAE, and we'll deal with computational biology problem with noisy data. And when we arrived at INRAE, all the things we knew about CP were difficult to use, and so we decided to extend this purely Boolean framework to a more numerical framework. And there was already the max CSP and the weighted CSP, but it was not superbly defined. And I just want now to give you our useful definition for what a Const function network is. The name says it. Instead of having a network of constraint, we have a network of cost function. So we keep the same set of discrete variables. We keep the set of functions, but instead of having Boolean functions, we will have integer functions. So numerical information, but something that can be represented correctly inside a computer. And exactly as in the previous case, each function involves a subset of all the variables, a subset S, which is the scope of the function. And it outputs an integer, and this integer is assumed to be bounded by an upper bound, k, and you can think about it as the maximum amount of money you're ready to spend on your solution. So if you have 1,000 Zorglub in your pocket to pay for your design, and if you have to pay 1,001 Zorglub, then you cannot pay 1,001, and your k will be equal to 1,001. Actually, it can be finite or infinite, but usually we use finite value for the upper bound. And so we have all those small functions which are bounded by k, and we simply sum them together. We sum them together, but remember k is an upper bound, so we sum them together and we cannot go beyond k. So if the sum of the number go beyond k, we are stuck at k. So we have a maximum threshold. I have these small operators plus k and some k here is just a bounded addition. You add up the numbers, and if they exceed k, replace them by k, and that's it. And so in this sense, you can see that a cost function network, what does it represent? Before asking any query on it, what does it represent? It represents a joint function, which is just a numerical function, which is bounded, upper bounded by k, and that's it. So we are describing a joint function. And now you can consider one problem on cost function network, and the weighted constraint satisfaction problem. It's NP-hard, or it's more precisely decision NP complete. And the question is, what is the minimum of this function? So it's exactly the same questions as for constraint satisfaction, but we have more values at hand. We are not dealing with Boolean function, we are dealing with numerical function. So the minimum will be possibly harder to find because the set of values is larger. And we can revisit the language. So I will, for clauses, I won't say anything because for clauses, it's very simple. I said clauses forbid just one combination of value. So you can simply associate a cost with a clause. It defines a weighted clause, and that's it, it works. For us, in our case, it's exactly the same. Previously, we had tables of Boolean, and now we will have tables of integers. So this is the same soft equality, let's say soft, because possibly we can violate it. But if I choose the same numbers for the two variables which are connected by this function, The same number, I have to pay 0. It's great, nothing to pay. If I choose different values, I have to pay 1. And that's it. Just a table of costs, of integers, and it defines a cost function. Naturally, in toolbar 2, you will also find so-called global cost functions. So using a specialized language, so you have soft or different, for example. You have this weighted regular functions, which uses a weighted automaton and generate a cost which is associated to the cost that the automaton gives to the words that that the sequence of variable defines. As I said, we will not dig into global functions, but there are references in this tutorial on these global cost functions. And yes, this framework or cost function network is quite general. We obviously like it. We usually make some simplifying assumptions inside the solver, and more generally, when we think about a cost function network, we think that we restrict ourselves to a subset of what I just presented. We assume that the costs are non-negative. This is useful for algorithms, as we will see, but it's not really important. I will explain why. If you make this assumption that all the costs of all your functions are non-negative, then a constraint is just a cost function that maps only to value 0, which represents true in some sense, and the value k, which represents false in some sense, violation, extreme violation, intolerable violation. And with these two items, you are guaranteed that if you have a tuple, a combination of values somewhere, which is mapped to k, it will be forbidden. So you have not lost the power of CP. The power of CP is still there. You are able to express constraint. Actually, if you set k to just 1, then you are reduced to a situation where you have only two costs available, 0 and 1. 0 is okay, 1 is forbidden. So essentially, you are falling back onto constraint networks. 0 represents true, and 1 represents false. It's a bit unusual, but it's perfectly fine. It's a pure convention, so it's perfectly fine. In practice, I say that the assumption of non-negative integer cost is not important because, well, we are optimizing, and we can multiply all costs by something, by a large constant. It will not change anything to the optimum, to the optimal solution. And so in practice in toolbar 2, we use very large numbers to represent costs. This means that we have around 19 digits available to represent a number. And if we decide that 6 of them are behind a decimal point, it's okay. So we can scale and play with decimal points instead of integers. And negative numbers are okay too, because if there is a negative number in a table, we can shift the table by a fixed amount to make everything positive. And again, it will go smoothly. All our table will be positive and our algorithms will be happy. And so if we can deal with negative numbers, we can deal with minimization and maximization, because if we only know how to minimize, but if we have a maximization problem, we just have to take the negative, the opposite of all the costs in our problem, and minimizing on it will actually maximize. And so forget about all this. We can express negative and decimal information, but inside the solver, everything is non-negative integer. And actually, we have a lot of additional assumptions inside the solver, which are important in practice. And again, this is without loss of generality. We always assume something which may look silly at first. We always assume that cost function networks have a constant function. That is, it's a function which has an empty scope. It depends on no variable. And this may look silly, but it will be useful, as you will see. If you don't need it, it's okay. Just set it to 0 and everything will go smoothly. Then we further make another assumption. We assume that all the variables in your problem, they have a UNARE, so a function that has only one variable as a parameter. So I denote phi. Phi is a function that only has xi in its scope. And this unary cost function, which depend only on one variable, we essentially use them as domains. So essentially, for example, if phi I on a given value u of the domain of variable xi is equal to k, the forbidden cost, it means implicitly that u is being deleted. And you can explicitly delete it, of course, but the information is in the unary function actually. And we also assume something which is more usual, that all functions have different scopes. Usually, in most cases, toolbar 2, when it sees two functions with the same scope, it merges them automatically using the combination operator, which is the bounded addition. And with all those assumptions, there is a very nice and crucial property, which is again silly and stupid and naive, but which will be very handy later, is that the constant term here, this function that depends on nothing, it's just a number. It may be 3, 5, or 10, whatever, it's a constant number. But for sure, because you are adding up non-negative numbers together, if you add up non-negative numbers together, these things can only increase. So this phi empty set is a lower bound on the join function phi m that is defined by the cost function network. It's a stupid and naive lower bound, but we will later improve it. So in practice, toolbar 2 accepts many formats. It accepts a very old WCSP format, which can be read very quickly, but it's quite hard to debug and to understand. It takes also CNF, so SAT, and weighted SAT problems, because yes, it's a specific case of it. It's not as good on those problems usually as MaxSat solver, of course, but sometimes, who knows, it can be better. It also takes quadratic pseudo-Boolean optimization problem, because all this is tightly connected to quadratic programming, as we will very quickly see. It also accepts OPB, so pseudo-Boolean, because it's also tightly connected to linear programming. And then it accepts those strange formats. UAI is uncertainty and AI format, which is used to define stochastic models. So toolbar 2 is also connected to probabilities, which will be very handy, as we will see. In this tutorial, we will be only using two other formats, a recent format that we introduced, which is called the CFN format, not surprisingly, which is sort of JSON-like format. It's JSON compatible, but it's more tolerant than JSON. It's more friendly, but so if you use this friendliness, you lose the JSON compatibility, of course. And also a very recently introduced Python API. So I say evolving because nothing we will use today probably will exist in 2 or 3 years. The Python API will evolve, and it will be much better than what we will show. And we will use only these two. And as an example to introduce these formats and this API, I will take a very simple and polynomial problem, which is a min-cut problem on graph. So min-cut, max-flow, you know, are dual problems probably. So, and the min-cut problem can be solved by a max-flow algorithm. And imagine I want to solve a min-cut problem on a graph VE with an age weight function W. What I can do to model it as a cost function network is simply to create a Boolean variable per vertex. And the Boolean variable will say, okay, you want to cut your graph in two, and you want to minimize the edges that are separated by this cut. So it means that you have to put each vertex either on the left or the right side of the cut. And so the Booleans say whether the vertex has been put on the left or on the right side of the cut. And then you have a cost function per edge. It's simply every edge in the graph will be represented by a cost function. And the cost function is easy to define. Essentially, if you put the two vertices in different sides, you have to pay for the weight. Otherwise, with this characteristic function, you pay nothing. And for example, on this simple graph with 4 vertices, you have the two sides of the cut, two sides for the flow, if you want to use a flow. So you have the ST, the source and target vertices, which are 1 and 4, and you can represent it by this cost function network. So I will spend a little time to explain what this representation is. It's usual in CP, in CSP, it's called the microstructure. It's a sort of variant of the microstructure. Here, each vertex is a value. This is a variable. And so this represents the two sides of the graph, of the cut. So we have a Boolean variable with 2 values. and each one for each of the three vertices of the four vertices in the graph. And there is an edge between two vertices or two values if we have a function that gives this combination of values a non-zero cost. So it's the opposite convention as in constraint satisfaction. In constraint satisfaction, you put an edge where things are authorized. Here, we put an edge where things are not completely costless. As soon as there is a non-zero cost, there is an edge. And just to exemplify that we can use decimal costs, I put a 1.5 cost. And you can see that if I put x1 on one side and x3 on the other side, I have to pay 1.5 because this is the cost of the corresponding edge, and they are on different sides. If they are on the same side, no cost. I didn't cut the edge, so it's okay. And this is the CFN representation of this problem. So yeah, as I said, it has only a few fields. The problem gives the name of the problem, the direction of optimization, the value of the upper bound, and the number of decimal we intend to represent inside the solver. So here it's saying that, okay, the upper bound k is 100 and numbers inside the solver will be represented with one decimal. Then I declare the variable. You see that I have forgotten the small quotes here, but so it's not JSON, but it's okay with the reader. It will accept this. Just to show you. And again, we define the name of a variable, its domain. The domain is just a list, a JSON list with a set of values. It can be shorter than this. You can put an integer and it says that there are this number of values. And this is it for the four variables. And then we have the functions, of course, and each function has a name. It has a scope. A scope is a list of variable names or variable indices. And the cost is just a table, as I said. It's a linear list. It's not a structured list. You can think of it, if you know NumPy, you can think of it as the flattened version of the NumPy arrays that correspond to the matrix, even if they are multi-dimensional matrices, of course. And this is it. Of course, this represents the fact that if we choose different values, you have to pay for it. And if we choose the same value, we are on the diagonal and we pay nothing. So this is the CFN version, and this is now the Python version. So if you use Python, you just have to import the cost function network package, and you create a cost function network object like this. So my CFN will contain a cost function network, and this cost function network can be initialized with actually there is only one compulsory argument, which is the first one, which is the upper bound. So the upper bound will be 100, and this is the resolution we want to use on numbers. So one significant digit after the decimal point. You can have additional arguments that specify which propagation algorithm you want to use, but I will not use it in the test I present. Simon probably use them. And so you have small function like this. For example, myCFN.getUB will return you later the upper bound, the current upper bound we have on the problems as a floating point number, the representation of the decimal point here. Then you can add variables. So for those four variables I have to create, I will create them with add variable. I just give a name to the variable. So here it will be x1, x2, x3, and x4. I give the domain. It's a list. It can be a number also. And in this case, if it's a number, it will just be, it says just how many values the variables are. And it returns a variable index if you want to use it later to designate the variable, but you can also designate it by its name. And then you add functions. So for example, this first function here it's a unary function. It involves only variable x1. And it says, okay, the first value of x1 has cost 0, so it's authorized. The second value has cost 100, which is our upper bound, so it's forbidden. It's essentially here to remove explicitly the side R of the vertex because it was as our source vertex. This removes the left value from X4 because it is our target vertex in the max flow or in the max cut problem, in the min cut problem. And then we have to add the pairwise function, and this is exactly the same. We give the scope, we give the table, and okay, you can pass a list, you can pass an NumPy array which has been flattened. It should swallow it without any issue. And when you are finished, so you need to add a few more functions. Of course, I just try to limit the room on the slide. At the end, you can solve your problem. You call toolbar2, and it will return a triple or none. None means that it found no solutions, everything at the cost above k, so no solution, above or equal to k, so no solution. But if it finds a solution, it will return a triple. A triple, the first element will be the solution as a list of value indices. The second will be the cost of this solution as a floating point. And the third one we don't use, it's a number of solutions when you do counting, but we will not do counting in this tutorial, so we can forget it. And so I will try now to start my VM. I'm on a fresh new machine, so I hope everything will work. But essentially, yes, we will now try to use toolbar2, the Python API of toolbar2, just to show that it's CP compatible and codes the Sudoku inside it. Something very, very easy. So if you think about the Sudoku, we will have to create variables, one variable for each cell. The domain of those variables will be the 9 numbers that you are authorized to put inside the cell of a Sudoku. Then you can imagine that we will have scopes. You want to define the constraints on row, columns, and these 3x3 subcells. So you will have sets of variables, a set of variables that contains the row, I, the same thing for the columns, column J, and the same thing for the subcells. By 3x3 subcells, you will have 9 of them. And essentially, if you were doing CP, what you would do is just put an all different constraint on each of these. And this will do the job very finely. All different is a very powerful constraint. It propagates very well, and it would make a very efficient Sudoku solver. Because I want to insist on those tables, which are useful, we will do something very simpler. We just will add a click, so a complete connected graph or pairwise different constraints. That is, we will take each pair of variables in those scopes, and we will post or define a difference constraint on this. We source these matrices before, and so let's try to write this as a toolbar2 Python API program. You can try to start your VM now, open a terminal in the VM, and from them enter the Sudoku directory, and I will try to do the same. So I don't know, how can I stop my, yes, I can stop. I will open a terminal here, and I will start VirtualBox. But not immediately, but soon, and I will start the VM. It's not exactly as how I expected to do it on my laptop, but it seems to be okay. So the virtual machine is starting, and things will be slower than on my laptop also, but okay, it's okay, because it's a big machine, but it's not a super efficient machine. So the VM hopefully will boot. And what can I do in the meantime? Well, not much I can say. Maybe I will go back to this. It's okay, it's starting. I'm reassured. Maybe we will be able to do something. I will keep this simple example here because it gives the main name of the function. And let me look into my prepared stuff here. So this is the first time this VM is booting, probably. So it will take some time. And Okay. Please boot. So essentially, we will be using only this. We'll create a cost function network. We will add the Sudoku variables to it. And we will add the difference constraints, clique of difference constraint to it. Then we will take an existing Sudoku problem from a set of Sudoku problems that has been used in benchmarking for other types of learning problems, and we will solve it just to check that we get the correct solution. So this is something very simple. Yeah, oh my God. Yeah. Aha, yes. Okay, next step. Okay, let's put this here. And let's put this here. It's okay. So I open, as I said, I open a terminal. I will try to make things a bit larger, just so that you can see. As I said, I will go to the Sudoku directory. And inside here, you will find a few files. So they are explained in the README, but we won't enter into this. If you want to go to it later, you can. Essentially, I want to introduce the two main files here. This satnet.csv.xz file is actually a set. We can look into it. So it's a CSV file, a comma separated value file, where there is always pairs of strings. The first one is a Sudoku where 0 represents the absence of solution, the absence of value. So it's an empty cell. But if you have a 5, which means that the corresponding cell is set to 5, and it's lexicographically ordered. So you have 81s of those numbers. And here is the corresponding solution, the Sudoku solution, the unique Sudoku solution. So you see that all the 0, which were empty, have been replaced by numbers. And we will use this inside the Sudoku problem. So let's now have a look to the Sudoku problem. Let's say it works. Okay. So it will be a bit smaller, a bit too small for you probably. So forget about code. Yes, I will just use less. And this is a solution, a partial solution to the Sudoku problem. And we will quickly look into, so essentially there are 2 lines in these files which contain this XXX question mark string, which says that something needs to be filled in here, it's missing. But I just want to go through this source very quickly. So we import the CFN package, as I said. We import NumPy because it can be useful. We import mat because it can be useful. itertools is good to iterate in sets. It's good to, for example, to enumerate pairs. And we import pandas. Pandas is a package that allows to read a CSV file very easily. And we can go through, actually there is 1, 2, 3, and probably 4 x66 in this file. And we can essentially first look into the main part of the program. You create a cost function network. You have to define the upper bound you want to use. We are doing CP, so you probably know what the upper bound is for solving CP problems or CSP problems. Then we will load a solution from the satnet example, and we will separate the ints where the incomplete grids are defined and the solutions where the solutions are defined. From this, we can extract the size of the Sudokus, so they will be 9 because they are the usual Sudoku. And the square root of this is the size of the subcells. So there are 3 by 3 subcells. And then we define the grid that we want to solve as a list of 81 numbers. Essentially, we transform the string of characters into a list of integers. There will be a 0 for an empty cell and a number for the cell. And we construct the scopes. So we have the set of rows represented as lists, the set of columns of the Sudoku represented as columns, and the set of cells, 3 by 3 cells, the 9 subcells, which will also be represented as list of lists. And then we go, and so we will create the variable first. And it's again quite easy. So we know that we have a 9 by 9 Sudoku. So we have two loops which go over the rows and the columns. And we need to create a variable. So this is where something has to be filled in. Again, we need to create a variable and store the results in the corresponding we will get the indices of the variable and we store it. And essentially we put this index in the corresponding column, in the corresponding row, and in the corresponding subcell. This is just simple arithmetics, and for the cells, we are using the integer division to find the right cell where we need to put this the variable. Now that we have these three series of scopes, we just click all different constraints on each of the scope. So on every row, every column, and every subcell. And once we have done this, we have essentially our Sudoku problems, and we just need to fill in the ints that were in the grid. So essentially, we use this grid variable, which contains 0 for empty cell and non-zero for non-empty cell. We look if we have a 0 in the cell. If we have a 0 in the cell, we do nothing. But if we have something else, something different from 0, we will add a constraint, a cost function which represents a constraint to forbid all the values but h. And then we solved and we print the grid. So this uses a few functions. So print grid is very easy. I don't want it. It just prints the grid of Sudoku with proper spacing and nothing really difficult. So don't look into this. It's not interesting. But there are these two functions which you could try to complete. So I will give you, let's say, 5 minutes or maybe only 3 minutes to try to fill in this XX question mark here. So the question mark, this function is supposed to add a clique of different constraints inside the CFN, which is passed as first argument, using the list of variables, the scope that is passed as second argument. And for this, we used itertools. Itertools is able to enumerate all the pairs inside the list. So it will enumerate all the pairs of variables. And of course, we just have to add the functions on those scopes with the different table. So we have here we need to have a cost table, a table of costs, which represents the different constraints. And this is what you need to define on this line. The second function you have to modify is the so-called setInt. Essentially, it takes a cost function network as argument. It takes a variable indices as argument, and it takes a value. And the idea is that you want to forbid all values but this one. So essentially, you will have to, we start from a cost, which will have some default values, which means forbidden for every value. So it's an array of size 9, of course, but it takes a value different from 0 on all positions. And then we just authorize the value. I put value -1 because inside toolbar 2, all values are indexed by from 0. So the number 1 is represented by 0 and the number 9 is represented by index 8. And then we add the function simply. And essentially, in addition with this upper bound and this creation of variable, this is it. I will let you try to solve it for a few minutes, and then we will look into the solution, because the solution is in this subdirectory, so we can look into it. So yeah, let's try to solve this, maybe starting with this one. What would you put here? So remember, the argument is the upper bound we want to use, and we are trying to solve a CSP, a constraint network, therefore. So it's a Boolean problem. We don't have any numerical information to give. And so we don't need decimal point number, of course. And we just need to be able to forbid something. And so you will guess quickly, I guess, that here the solution is to put a 1. I will say it because we have, yeah, it will be long otherwise. This is it. So here we just put 1, and we know that we are doing CP actually, not cost function network in general. Here I have to create a variable, and it's again quite easy to imagine what you have to put. In my Python API here, I identify this function, add variable, and let's make it a bit bigger. And well, add variable, you have to give a name and a domain. Of course, here we will give the name we want. It's not important. For example, we could put xij with the two parameters to give the position. And the domain needs simply to be a list of 9 numbers. It could be also the number 9, just the number 9, but we can put a list of 9 numbers from 1 to 9. And we will see this in the solution. And then we go back to the function above. So how can we define a table that represents a difference constraints between digits between 1 and 9? Well, essentially, we'll need a matrix, a 2-dimension matrix, and the 2-dimension matrix should forbid equality. And equality means that we are on the diagonal. So it's funny to see that difference actually will be represented by just an identity matrix. We just need an identity matrix, and the identity matrix can be interpreted as a difference constraint. And that's just what we will need here. And with this identity matrix, we will flatten it to make it toolbar 2 flat, and we will add it for every scope, and this should do the job. Then here, which cost we want to forbid all the value except the one which has been observed in the grid. Essentially, we will create an array which will contain 1 everywhere, and an array of size 9, obviously, because the Sudoku has 9 possible values in each cell. And then we know that the cell must contain some given value, and we will, at the corresponding index in the list, we'll authorize this value. And the simplest way to make it fully authorized, it would give it the 0 cost. So like true in Boolean interpretation. And I think this is it. And I will copy the solution and here, and I will try to execute this. In this case, it will read just the first grid of the SATnet dataset that contains actually 1,000 grids, and it will try to solve it. And it prints the empty grids, and then it prints the solution. And it works as expected. It's quite efficient even in the VM. What you can notice is that these grids are very dense. There are many ints. It means that actually those SATnet problems are very easy. On average, there is 36.2 ints per grid, which makes them really very easy. And so we can do CP. We can do CP with cost function network. It's okay, it works. And we go back to the slides. Up. So we saw this. And now, just to see what the cost function network makes possible is to try to see if we can connect this simple Sudoku solver to analyze images instead of grids of numbers. So what we can imagine, and I know TIAS will do the same thing tomorrow, but we publish this in CP this year. TIAS published something similar in CP IOR, so we did the same stuff with different targets. Our target was learning, his target was solving. Here we will do solving as he will present tomorrow. We will do something much simpler than TIAS, but essentially the idea is to take an image of the Sudoku. We have digits, 110 digits everywhere for ints. We will submit this to LeNet, which is the most famous and a bit obsolete, but still working convolutional neural nets. And what LeNet does when it sees an image like this, it produces an array of costs, actually. I shouldn't call them costs. It produces an array of scores, which says, okay, does this number looks as a 0? Does it looks as a 1? Does it looks as a 2? Up to 9. And so it produces an array of score, and the maximum score is the prediction. So here we assume that the net will work correctly, and the 6th score will be the maximum score. And so we can decide to predict a number, it says 6, and from this we can create an actual numerical grid. It's no more an image, it's now an array of numbers with all the predictions. We can send this to a CP or a CSP solver and it will solve it. And this is the first things we will do. We will use Booleans. We will assign the cell with the prediction of LeNet and we will try to solve. LeNet is a very good convolutional net. It has a ratio of success in the version we will use, because there are better versions, of around 99.2 or 3% success. So it fails very rarely, but sometimes it fails. And when you have a grid of 36 numbers to decode, it has 36 opportunities to fail. So we will see how it works in this case. Obviously, when LeNet fails, the ints are false. There is at least one false int, and the CSP or the CP engine will have difficulties in solving the wrong problems, of course. I would like to show then another very simple path, and it will be extremely easy to change from one to the other. Instead of predicting and not dealing with the uncertainty of the output of this machine learning machinery, we will use the scores here. Not exactly directly, because the maximum score is a predicted number. We are minimizing by default in toolbar 2. So we will negate the score. It's very simple. We just negate it. We take the opposite. And once you take the opposite, it's obviously the minimum score, which is the best. And the other scores are less good, but they give an information. Actually, it can be somehow, yeah, it can be after normalization and exponentiation. It actually in the wrong order, after exponentiation and normalization, it can be interpreted as a distribution probability on the output. You may want to calibrate it. We will not do it. TIAS will do it tomorrow, I think, because I read this paper, but we won't do it. It will be very simple. We'll take the output of the neural net and we will feed it after negation into the cost function network. And we will see how it works. So let's try this now and see what it gives. So I change directories and I go to the Sudoku deep learning CP directory. I clear everything and I will list this file. So just to explain you what I have in this directory. So the data directory here is just a directory that contains the NIST images. So nothing, just to show the Sudoku grid. SATnet is the same that we saw before. The NIST train algorithm is actually a PyTorch script, which we do the training of LeNet. I have already executed it. When you need to use it, you need to produce the only stuff that actually toolbar 2 needs to solve this problem. Actually, it just needs the output of LeNet, this array of scores, actually the negated array of scores on every possible image of the test set of the net, which is in this data set. And so this is a pickled, so I hope you know pickle inside Python. Otherwise, let's say it's a compact representation of an array of score for every number in the NIST handwritten digits test set. And we just need this for toolbar 2. If we have a 1, we need to pick up someone in the NIST data set and see how well does the net on this, get the output and feed it into either a CP version of toolbar 2 or the cost function network version of toolbar 2. And I will just show you the code. There is no exercise here. I will directly show you the code of the most important one, which is this one, which actually solves this. So we do import the CFN, we import other stuff, nothing important. We import torch and torch vision because we want to read the images. ITER-tools again for the click of difference, pandas for CSV, hashlib to make things reproducible, nothing important. These are image output routines. They are not interesting, just matplotlib to produce images, nothing interesting. Here again, we are reading the data from NIST, nothing interesting. You may want to look into it if you know PyTorch. It's nothing crucial. Then perhaps this one is useful, it's important. In the logits variable, we will have the output of the net on every possible digit ordered in the list of 10 elements for 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. For every possible representation image of the corresponding digit in NIST. And this table says how many images there is for each number. So there may be 101, 102, and this gives it. This is for producibility, my hash. This is the same, and the most useful function actually for our, so you see the x66 again here, is this one. It's very simple. It takes as argument a Sudoku grid as a character grid. So CG is for character grid. So exactly as we got it from the CSV file, it gets a position between 0 and 80 inside this grid to designate the cell which we are interested in. It takes the value that is contained in this cell, and it will return you the output that the net will produce if we give it this number with this the corresponding image. So this is this is just the output of the net in some sense. So we load the Sudoku grid as previously from SatNet here. And then we have the same function as before. So we saw that we use this identity matrix, as I say, we flatten it, and we thus multiply by the upper bound to get the constraints. Same function as before. I didn't show this previously, but also the cost to forbid values. We use a matrix which is equal to 1 everywhere, a matrix of size 9, and we put a 0, as I said. And then this is a crucial function. Instead of using this function, we will not use this function. We use this function in the CP case. In the CFN case, we will use another function we will see later. So the program takes some time because it loads torch, it loads the MILS data, it loads the SatNet test set. So it takes some time to boot, to start, but then afterward it expects one argument, which is a grid number. There are 1000 grids in SatNet, and it will just do its work. It will do exactly as we saw before. It will create the variable with the correct domain. It will put the all diff constraints. It will get the prediction of NIST, and it will take the argmin, as I said, because we have inverted the score, negated the score, and it will simply just put the corresponding constraints. It's here. It will put the constraints that the variable, corresponding variable must take the value that is predicted by the net. And we solve, and this is it. And so let's see first the CP version. And so we can just do simple stuff. we apply this on the, let's say, the first grid, well, the second grid actually, but the grid numbered 1 in the SatNet test. And so, yeah, so it processes, and we have it. So we have the solution. This is, why can I, yeah, because this is the image and not. So this is it. We have the solution. The dark cells are the hints and the white cells are the solution. And you can see that it solves this problem very well. Why cannot? It's funny because I cannot play with my, yeah. Let's say I want to quit. Okay. And this is the optimal case. CP works. Now let's play with this next grid. So we will take the second grid in the SatNet dataset and just use CP again. And then it fails. It fails. Why? Well, the colors indicates here that this number, which is a 2, has been predicted by LeNet as a 7. And because we have another 7 here, it makes the problem infeasible. And so CP just says, okay, you're stupid, your problem has no solution, so no solution found. And that's it. And actually, you can find that there are many grids like this, the same for grid 6, for grid 10, for grid 16, 17, 30, 31, 32, 37, 40, 44, etc. There is a very high percentage of grids which cannot be predicted by CP in some sense. And so let's shift to the richer cost function network version. So CD, we go up and we try with the Sudoku deep learning CFN, and I know CFN. There was an exercise here also. Let me just show you the data. It's exactly the same thing. I will avoid the exercise because I'm afraid we will be too late here. So if you want to look into it, look for the XXX question marks. I will just copy the solution here and show you the most important part of the code. So we have the same image code, we have the same data loading code, the same Sudoku Grid code, but the main difference is very tiny. The first difference is instead of using 1 as an upper bound, I choose 1 million here just to be safe. It's a huge bound. It's a big M, as we say when we do ILP or LP. It's a big M, and here we choose a resolution of 6. That means that we are ready to cope with decimal number, and we will represent decimal number with 6 digits after the decimal point. So toolbar 2 is ready to play with floating points in some sense. It will convert the floating point and run them to the nearest decimal, the roundest decimal point it can represent. And then the only difference is that instead of setting the int, we will set a probabilistic int. Simply, we will add a function, unary functions, which directly takes the output of LeNet, the negated output of LeNet, and add this as a function. And this is it, nothing more. So this is the only difference we need to change compared to the previous program. We change the upper bound to be able to play with decimal numbers. And we change the previous unary constraints to a unary function, which is just directly the scores, negated scores of LeNet. And how does it work? So same argument. Let's say that's right, Python 3. Let's play with the first grid, which was solved by CP. Of course, we solve it also here, and we get the correct solution. Nothing surprising. But what does it give on the second grid? The second grid where CP found an inconsistency. And so, yeah, it reloads the images and everything each time. And you can see that we have the solution here, actually. Because when there is purple, it's bad. When there is black and white, it's good. And where there is green like this, it means that actually toolbar 2 decided to correct the solution. So it got a distribution of scores. The distribution was saying that it's a 7, but this was incompatible with the 7 here. So it tried to correct it optimally and choose the next compatible number in the scores by optimization and replace and corrected the error and found the correct grid. And actually, this is the same for almost, I can take, let's say 50, for example, and it's the same. There will be an error. CP couldn't solve it, but this numerical approach, yeah, corrects the 4 here, which was predicted as a 6. But it does not work everywhere, but you have to go further in the list of problems. And this one, I think, we will get the wrong solution. So you see there are 6 numbers which are wrong because the 9 here was predicted as a 5 and actually didn't correct the error, and he preferred to correct to solve a grid. So it's a correct Sudoku answer, but it's not the correct one because there is a solution which is compatible. And so this happens also, and you can, and this is it. And so Thias will show you how you can do better stuff tomorrow with calibration, something which is very usual in machine learning. And so we can. I see nothing with this stuff. Let's move this. I hope this has motivated you to learn what, yeah, it took quite a time. Now I want to show you, yeah, this corresponds actually to the hybrid one of Thias. Thias uses a COP solver, so constraint optimization problem solver. It takes 0.8 seconds to solve these problems. Toolbar 2 takes only around 50 milliseconds to solve them. Actually, on 1,000 problems, 996 are solved backtrack free. It means that really the lower bounds that a cost function network use are much tighter than the COP bounds. And this explains why Toolbar 2 won actually several approximate probabilistic inference challenges. And you may wonder why probabilistic inference, but you saw that we can deal with probabilities in some sense by taking the logarithm. And in fact, there are probabilistic models which are called Markov random fields, which are used in machine learning and in computer vision to actually represent specific functions. And these specific functions are probability distribution, complex joint probability distribution. And it's funny to see how close Markov random fields are to cost function network, even if they evolved independently. Markov random field in their discrete variants have a set of discrete variables exactly as cost function network, and they have a set phi of non-negative real valued cost functions. So instead of integers, they are reals, which don't exist in computer, but okay, we can approximate them with floating points. And again, usually they are described as tables, exactly as this cost function network. And Markov random field can be used to define a probability distribution simply by taking the product of all those non-negative real valued functions. If you take the product of plenty of non-negative real valued functions, you get a huge non-negative functions, and you just have to normalize it. And you get a probability distribution. Of course, the computation of this normalization constant is a pain. It is sharp hard to compute. And we will see how we can deal with this. But actually, to solve optimization, we don't mind about this normalization constant. So maximizing the probability of an assignment or maximizing the cost or the energy, the opposite of the energy, as they call it in or the non-normalized probability in this case is the same. So we don't have to take care of this normalization constant. So essentially it means that Markov random fields can be reduced to cost function network. So multiplicative Markov random field can be transformed into a cost function network that use an infinite upper bound just by applying a pointwise minus log function on every cost. You transform the multiplication with minus log, you transform the multiplication into an addition, and you transform the maximization into a minimization. It does the job, and actually it's known as the energetic representation of a Markov random field inside Markov random field. If you do x minus 6 instead, you go back to a Markov random field, and this is the Boltzmann transformation. So in the end, what you can remember is just that solving WCSP on a CFN with an infinite upper bound is the same thing as solving map on MRF. And this is one link, one connection. I said I would try to show a connection, and this is a clear connection. People in MRF, in computer vision, some of them know this connection. There is another connection. I promised I would talk about LP, so linear programming, and obviously solving this WCSP problem can be also, it's an NP decision NP complete optimization problem, so it can be solved using integer linear programming. And there is a very famous formulation of the pairwise weighted constraint satisfaction problem as an ILP. It even has its relaxation, its continuous relaxation, has even a nice name. It's called the local polytope because it's an approximation of a more complex marginal polytope. And it's quite easy to understand actually. It uses one Boolean, so 0, 1 variable per value of, so the value A of variable I will be represented by a Boolean. And what you say here is essentially, if we use a value, you have to pay for its cost. There are also value, again, 0, 1 variable values, y, I, a, j, b, which represents the value A of variable I and the value B of variable J. And if you use this pair of variable, you have to pay for the cost. So here we say that we want to minimize the cost because essentially the cost in a cost function network is a linear function of the cost. So it can be expressed as a linear criteria. And then we connect these two variables and we also constrain this variable. So first constraint is that, okay, if we have 9 value, for example, in the Sudoku, we must choose only one of those 9 values. So the sum of our Boolean must be equal to 1. And then we have extra constraints that connects the pairwise variable with the unary variable, let's say. So if we use the value, of course, we must use one of the corresponding pairs and vice versa. And this in the two directions of every constraint, every pair of variables. And if you add the fact that this x should be 0, 1 variable, it's a perfect and actually a quite tight polytope that captures the WCSP. If you relax, it defines. If you relax these integrity constraints, it defines a quite tight polytope. It's a strong bound for optimization, but it's very expensive. You see that the size of the problem is not small. It's a bit better for the dual, but still big. And so you have this connection with ILP and LP, and we will see it again. Actually, I will not spend time on this, but it has a much tighter, much simpler and dense formulation as a quadratic program, because then you don't need the y variable. You just take the product of the two Booleans. It will be equal to 1 when both values are used together. And then it's a very dense quadratic program which says something. It says that when we are solving a cost function network, we are in some sense solving a quadratic programming problem. And actually, as you saw, toolbar 2 can read quadratic pseudo-Boolean optimization problems because it can solve them. And this is it for the connection for now. We will also use some fundamental notions or functions. So we'll say that two functions are equivalent if they are always equal. This applies both to functions, but also to cost function network, and because cost function network represent a joint function. The relaxation of a function, we will say that a function is a relaxation of another function if it's always smaller. It's usual in optimization. Relaxation is something that is smaller always. because usually you enlarge the space, but here it's just smaller. It's interesting to understand what this means where we are playing with Boolean. So where we are using Boolean, so CFN using the upper bound 1, saying that a function is a relaxation of another one means that the function phi prime actually semantically entails the function phi. So this notion of relaxation, which is very usual in optimization, it exactly matches this notion of semantic entailment in propositional logic. And in constraint satisfaction also, of course. So it's useful in this case. And we can now shift to algorithm. It will be very, I'm afraid I will not be able to do everything before the break, Simon. So maybe I will skip some stuff, I will see. So now the idea is to show you how things work, what algorithms are used to produce these tight bounds, and where they are tightly related to LP, to linear programming. The first type of algorithm we will see are essentially what I call conditioning-based algorithm, systematic search and local search. Nothing very fancy. And the second type of algorithm we will see are elimination-based algorithm, so local consistency and variable elimination. So conditioning. What do I mean by conditioning? Essentially, I mean assigning. This is the probabilistic version of it. If we have a function phi in our network, and we want to take into account the fact that we know, or we assume, that some variable takes some given value, we can compute a new function, a reduced function, which will be the conditional function in some sense, which is simpler. The scope of the function will be reduced by one variable because we know its value, and obviously the size of the table, which will be smaller. Let's see this of an example. Imagine I have a cost function between two variables here. So if I choose AA, it costs 1. If I choose AB, it costs 2, and so on. Imagine I know, or I assume, that x2 is equal to b. Actually, it means that I'm only interested in this slice of the table, and I can condition my function and get this function on the right. This function is simple. This operation is very efficient. It's just moving a pointer in a table, so it's negligible complexity, and it gives you a new function. Actually, you could do this again. You could condition on, let's say, x1 equal b, the second value, and then you will get a function that has an empty scope, like phi empty set, and it will be a constant term equal to 1. So you see that this constant function can pop up just by two conditioning. And with this, we can do backtrack or branch and bound search. Essentially, we observe the fact that if we have a cost function network where all the domains have size 1, it means that we have no choice. It's very easy to find the minimum. We assign all the variable with their corresponding values, and this is it. Essentially, we found a solution of a given cost. If not, we choose a domain, a variable with a domain of size greater than 1. We choose a value, and we can split it. This is a usual branching rule. There are other rules, but this one is useful. In one side, we assume that the variable is assigned to the value in the domains of size greater than 1, and on the other side, we remove the value from the domains. And we solve these two queries, the two optimization problems, and we return the minimum of the two, and this is okay, it will work. This algorithm, as it is obviously exponential time, although it's space efficient, it's exponential time, it's completely useless, and it's easy to improve it a bit if we have this magical object, which is a local lower bound. That is, if we have a lower bound for each of the problem we want to solve. when we want to solve this query, we would like to know beforehand some properties of it. And if we know that the optimum cost will always be greater than some value, it's interesting to know. Why is it interesting to know? Because if we already know some solution, whose cost could be stored in K, if we already know some solution, then if this minimum cost is higher or equal to the best known solution cost, we can prune. And this is branch and bound. So, and we do have these two objects. As I told you, phi empty set is a lower bound because we play with non-negative functions, and K is our upper bound. And each time we find the solution in the algorithm, we can update K to this cost to say, okay, we want better and better solution. And obviously, this algorithm strongly depends on the lower bounds. We can relax this pruning condition. We can do what is called, so we can do partial search or relaxed pruning, bounded number of backtracks, or as in CP, bounded number of discrepancies if we have a good value ordering heuristics. So essentially, toolbar 2 does tree search. Should we do depth first as CP, or should we do best first search as ILP? Actually, toolbar 2 is closer to ILP in his last versions. It uses a hybrid algorithm, which is called hybrid best first search, a nice idea by George, which we start by doing by diving into depth first search for a bounded amount of backtracks, like it is showed here. So we do a sort of depth first search, and at some point we have done enough backtrack, we stop. And we go back to the root, and all the pending nodes here, which have not been yet explored, are pushed in a list of open nodes. And then we start it again. We take one of those nodes, the best one, and we dive again. And we do this repeatedly. And the algorithm is more sophisticated than this. It knows how to exploit a nice graph structure here, where vertices are variables and edges are cost function. So it knows how to exploit this and sort of swallow them from the leaves to the root using branch and bound search. This algorithm is nice because it uses depth first search, it provides upper bounds very quickly. Because it uses best first search, when it takes the next open node, it produces an optimality gap. So we have an optimality gap that reduces as we solve. And it does in some sort makes an implicit restart because we restart. And we also do local search. Here I exemplified variable neighborhood search. In variable neighborhood search, or in all local search, most local search, all the variables are assigned or conditioned, and you choose a subset of the variable, so a subset of size S. You unassign those variables and you optimize them with some other algorithm. Once you optimize them, they will have new values, and you look if you have improved your global function, your join function. If you improved it, you're happy, you keep this new solution, and you reset the set of the size of the set you explore to a starting value, a small starting value. If instead you didn't find an optimizing move, you increase the size of your neighborhood and you shift, instead of unassigning 3 variables, you will now unassign 4 variables. And you go on like this, and we will use this later again.
Thomas?
So this is it. Oui?
I wonder if we maybe have time for a break.
On fait à 4h30?
Maybe we could continue on the modeling part and see if we speak about the algorithmic part at the end.
Yeah, I would be happy. I will skip the elimination part, but I would be happy to at least present the local consistency and its connection with LP.
Mm-hmm. Okay.
So I could start now. We make a break. I start over with this. I probably will stop there, and I will give you the microphone and the everything.
Okay.
Okay. So yeah, I just, because I promised it, I just would like to highlight the links with linear programming. And they are visible in the local consistency of cost function network. And so how do we enforce local consistency on cost function network? We use two fundamental tools, which are again quite simple. The first one is the ability to combine two functions by summing them together. So if you have a table of function on one variable x2 here, and a table of another function, which involves x2 and x1 these times, you can simply sum them together by taking the sum of the cost and defining a new table. This 5 here is here because 1 plus 4 is 5. This 6 here because 2 plus 4 is 6. This 7 here because 3 plus 4 is 7. And that's it. It's just combining by addition, nothing special. It's still a quite expensive operation because here the two scopes of the two functions were included one in the other, but essentially the size of the finite table you have to produce is exponential in the cardinality of the size of these sets. So it can be somewhat expensive. And the second one, so this is nice because it's combined information. Now you know that the optimum could be better here, and not in the middle, which was not visible here. The second operation is elimination, and elimination tries to reduce the size of the table by getting rid of variables. And because we know we try to optimize stuff, we can get rid of variables by assuming that they will take their optimal values. So imagine, for example, that I have this table, which is the table which I had here. I have this table, and I want to get rid of x2. I want to eliminate x2 by assuming that it will always take its optimal value. Well, it's easy. For the first value of x1, I have the choice between 5, 9, and 6. I will take 5. Here, the choice between 6, 7, and 7. I will take 6. And x, the choice between 7, 8, and 5. I will take 5. I can eliminate x1, eliminate x2, and get this simpler function. This is a dense representation of the effect of optimization and combination on x1 only. I can further eliminate x1 and I get the constant terms 5. And actually, it's the optimum. It's the optimum of this table. So you can see that by combining and eliminating, I can get the optimum. This can be used in two ways. You can do this on a single function. And this will, so combination accumulate all information in a single function. Elimination forgets one variable without losing optimality. And you can use these two operators at different scales. So we will skip this one, but we will try to look in this one. You can apply these two operators on very small subproblems which are defined by just one scope. A small scope, let's say the scope defined of one function. And this is what our consistency does. Our consistencies in CP, we play with one function. For example, in this case, imagine that this value of this variable has been deleted by propagation. If I look into this value, it is incompatible with this value because there is a cost of 1. It is incompatible here because this value has been deleted. And so I can decide to delete this value. This is our consistency, filtering by our consistency. If a value is such that there is no value in the other domain, such that the function is satisfied, we can delete it and we leave the problem equivalent. If we apply this repeatedly, we make all the domain consistent with the binary function and the other domains, and we get the famous R-consistent closure, which is unique, can be reached in polynomial time efficiently. And we can reinterpret this in terms of combination and elimination, simply as in relational databases also. The combination of this pairwise function plus the domain can be seen as combinations of the cost matrix with the domain, we get a combine join table, and we just eliminate the variable from which we took information, and we get new information on the variable x1, which is okay, you can delete the two values, which is exactly what our consistency would do here. It would delete this value, it would also delete this one because it has no support. The nice thing that I said before is that if we do this in the Boolean case, everything goes smoothly because the message we compute here, this is called a message. The message we compute here, it's actually implied by the constraint network because it's a relaxation, because we minimize, and we can delete value, it's okay, we remain equivalent. We can say that network is consistent when the domains contains enough information, so the domains are represented by unary functions, and everything goes smoothly. But with cost function networks, this does not work, because if we do this directly, we lose equivalence simply because we will create new one in our network. This one will add up with other ones and will create two, while we had no reason. So we will solve a new problem, a different one, and the optimum will not be preserved, and this is completely useless. And so the ideas we have several years ago is to nevertheless do this. So we will compute these small tables, this one here. We will compute it exactly as our consistency does. We will add it to the network. And to try to preserve equivalence, we will subtract it from its source using the inverse, pseudo-inverse operator of addition, which is defined here. It's very simple. It's a pseudo-inverse. It works as you expect, like a subtraction when k is infinite. Let me show you this on an example. This is a small cost function network with two variables, two values. An edge represents a cost of 1, an absence of edge represents a cost of 0. And here I have a unary function that says that this value has a cost of 1. And let's say that k is equal to 3 or 4, big enough. If you look to this value, and it has no support here, and you can decide to compute the message for this value. And the message will be to create a 1 on this value. You can create this 1 on this value, but to compensate for this addition, you subtract it from its source. So you delete these two edges. And you get the problem on the right. And the nice thing is that you know that this problem is equivalent to this one. Of course, you can go the other way around, come back on the central problems, and you can go on the other side. Look instead to this value. Again, it has no support here. There is a cost of 1 here, a cost of 1 here. So you can create a message that will increase this cost by 1. And we delete these two edges because that's a subtraction to compensate for the addition, which is here. And we get this into this problem, and this one is much nicer because, so we can go back, but we won't do this. Instead, we can take again, eliminate x1 and get a constant message. And this constant message, we say, okay, we have a new problem with a new constant term. And this problem is actually equivalent to this problem here. And by doing this small cost shifting operation, we can increase the lower bound. And so originally we had a small problems which had a lower bound of 0. Phi empty set was equal to 0. And by playing with cost like this, we get to a problem which has a lower bound of 1. And you can see that we can cycle easily, and it breaks a lot of stuff from CP. Things get non-monotonic. Sometimes often fixed points become non-unique, and they may even not exist. So we had to do some stuff to guarantee to remove all those problems. And I will stop very soon, I think, just and I will take 10 or 15 minutes afterwards to finish. Essentially, we worked a lot to try to break these loops, so to enforce fixed point existence, defining plenty of R consistency. And these R consistency are increasingly strong. So you have not consistency, R consistency, directional R consistency, full directional, existential, and virtual, which I will quickly describe. And each of these try to organize this cost move in larger scopes, I would say. So this one plays only in one function in one direction. This one tries to reason on a star, a variable in the middle of a star, and all the functions which are incident to it. And virtual AC, virtual AC, it plays on the spanning tree. And it's nice because at the end, when you enforce this, you have this notion of support, exactly as in CP. And you can say that a value has a support, an EAC support. And the support is, when you have them, it's very strong because you know that the unit cost is 0. And this cost can be extended for free on the star around Xi. And for VAC, it's even stronger. It has also a cost of 0, but it can be extended for free on any spanning tree. So it's really strong. And we can delete values based on what is called reduced cost pruning or back propagation. Essentially, if your lower bound plus the cost of a value reaches your upper bound, you can delete the value. And this slide, and I will stop. The nice thing is that it's a proper extension of R consistency. When you apply this on CFN of 1, it does what R consistency does. It's polynomial time. It is space efficient, exactly as R consistency in the classical case. It's incremental because it's a reformulation. It can increase our lower bound, which is very useful for branch and bound. And the lower bound can be stronger and stronger if you use stronger bound. Actually, what you have seen with the Sudoku example is that the bounds are, I can say, much stronger than what R consistency does with the global sum constraints in COP. The global sum constraints in COP with bound consistency, it's not very strong. And those bounds you got with VAC especially are much stronger. And of course, what is important is in which order you apply all those small operations. And the order, what we have shown with Martin, is that the order, if you want to find the optimal order for applying this operation, is NP complete if you allow only to move integer cost. But it becomes polynomial if you allow yourself to move rational cost. And here is the connection with LP. Which is probably when you relax your cost move to allow for rational cost moves, then you can find an optimal lower bound, essentially by using the local polytope we saw before. So this local polytope, which was the linear relaxation of the integer linear program that represents our WCSP problem, if you express the dual and you solve it, then you apply R consistency, then the dual, then R consistency, then the dual, because this cannot deal with infinite cost. It cannot play with infinite cost, but R consistency can play with this K cost. So you have to do this loop, and it will actually produce the strongest bound you can produce without creating the strongest bound that parameterize the network without creating new functions. And I will stop here. It's 4:30. I will just use a few minutes afterwards, let's say 10 or 15 minutes to better describe this connection with LP. And probably despite the many slides that are afterwards, I will stop there. So see you in 30 minutes.
Maybe we can make a shorter break of a quarter.
Yeah, I don't know, Christian.
Yeah. You feel free to shorten the break if you want, just a 10-minute break so that you can have more space for you.
Let's say a 15-minute breaks. 15-minute break.
Okay, so maybe
so come back at 4:45.
Can you take maybe one or two questions before the break if there are some?
Of course.
I don't know if the participants restrain themselves for asking questions during your talk. So if there are any questions, we can take one or two before the break. Otherwise, you can think about it and ask questions after the break also.
Sorry. We are several in the office.
We understand the situation.
You just heard my wife.
Okay, no participant raised their hands, so I think they are ready for break now. So it's 4:30 p.m. So let's meet again at 4:45
In
p.m.
15 minutes, yes.
In
Okay.
15 minutes for the continuation of the Simon and Thomas lecture. Thank you very much.
Thank you, Christian. I will skip many slides. I'm sorry about that. I underestimated the time for the Sudoku stuff. Presenting the Python API took more time than I expected. I should have rehearsed. I didn't. It's a bad idea. The slides which I will skip, it's not crucial because you have them in the CP 2020 tutorial. Which is available on YouTube, so you can have the video if you want, if you are interested to understand the variable elimination stuff, for example, and the performances on protein design problem, for example. So I was there. I was saying that this kind of cost shifting operation, it was difficult to organize them properly when you were doing integer cost moves, but it works fine where you are doing rational costs. And this is because actually if you write the LP that says, okay, these are my variable, the amount of cost I shift from each variable to a constant term, or from a pairwise function to one side of the variable, or from the other side of the variable. So you really take as decision variable the amount of cost you want to move, and you express the problem that say, okay, I want to move as much cost as I can to the constant term, maximizing the lower bound. But please do not create negative costs. And this is what these two constraints says. Please don't create negative costs. We don't want negative costs because otherwise the lower bound will not be a lower bound anymore. So we absolutely want the cost to remain positive, not negative. And if you look into this problem, you can realize that these three variables that we use are actually the dual, the Lagrangian multipliers that you need to put in face of each of these constraints. And so actually OSAC is sort of solving the dual of the local polytope. And but it alone, it's not sufficient. You have to use R consistency to deal with constraints also. So it deals with all the finite costs, but it does not deal with inconsistency. And you have to mix them together. And it can be quite strong. It can reparameterize, change this problem with no constant term to this problem with a constant term, and you can do that. It's doing quite heavy stuff. Huh? It's really doing a fine job. And I want just, I will just use then few slides afterwards to show you the performance of toolbar 2. But this thing is important because I think it shows the very tight connection we have with LP. We have all those small R consistency, which are very fast. And actually, seeing this, you can understand that they approximately solve the dual of the local polytope. So it's funny to see that if you extend R consistency to the weighted case, what you end up solving is approximately solving an LP. They solve it approximately. They have no guarantee to find the optimum, but they do this much, they are much faster than the simplex or an interior point method. And now they have used new results by Prusser and Werner in 2015, which says that actually these problems that we saw before, the local polytope, it's not just a specific LP. Actually, it's a very general LP. It's universal for LP. What does this mean more precisely? It means that any well-behaved LP, so bounded and blah, blah, and blah, blah, so not a strange problem with infinite rays and things like that, it can be transformed in linear time, not polynomial time, linear time, in a cost function network such that if you enforce OSAC, so not the R consistency part, but just the LP part, it will provide the optimum of the LP. So essentially, we have a very tight connection because you can transform any LP in a cost function network. And the bounds that we get on this cost function network will be bound on the LP. And then you have all those super fast local consistencies like VAC. VAC produces an approximation of this bound, but much more faster than LP does in general, much faster than LP does in general. And there is a recent paper by Werner again at CP 2020 that give some more fact on this connection between VAC and LP using the Farkas lemma. So I won't speak about this. Yes, VAC is interesting because it solves some modular function, so it solves min cut, it solves tree structured problem, it solves other types of problems. So really, at the end, when you do cost function network, it enhances CP with fast, incremental, approximate, linear programming dual bounds. That's a sort of general message. And this thing is really fast. Here, just an example where I apply Simplex on the formulation of a protein design problems. And you see that Simplex solves it easily. Yeah? It only takes 900 seconds to solve it. And the same hardware, the same model, which, yeah, universal, everything is, we find the same optimum, but it takes only 9 seconds to prove optimality because the bounds actually are, yeah, very limited number of backtracks. The bound is tight. We find the optimum very quickly, 2 orders of magnitude faster than Simplex. And actually, this is more general because people in computer vision wrote this kind of stuff. Toolbar 2 variants were superior to Simplex variants in all our tests. So on some problems, not all problems, of course, Toolbar 2 has some strengths compared to Simplex. We didn't compare to Gurobi, and neither did this guy. And another one from a famous protein designer, there's a Toolbar 2 package for WCSP significantly improves the state-of-the-art efficiency for protein design in the discrete pairwise model. I will skip this thing on VAC, show you how VAC works. This is not in the CP 2020 tutorial, it's okay. I will skip this. I said I would skip variable elimination, so I skip this. It's all in the 2020 tutorial on CP. I will just say a few words about this. Simon did a very large experiment taking problems from Markov random field area, computer vision area, our own library with bioinformatics, computational biology problem and resource allocation problem, max CSP competition, max SAT problems, CP problems, generated a huge number of benchmarks by encoding these problems in various formats, either for Simplex, so using 2 encodings, for weighted max SAT using 2 encodings, for Toolbar 2, for Markov random finite solver for CP. And he generated this very nice, and I will stop there after that, it generated this very nice diagram or plot, which on the x-axis, essentially you consider all those problems, there are a few thousands of them, 3,000 if I remember well, and you keep only the non-trivial problems, so those for which solvers take more than some fixed amount of time. And you normalize both the time it takes to solve those problems or reach the upper bound on time, on solving time. This is the X scale, this is the time normalized for all solvers and all encoding. And you normalize the score or the bounds or the optimum by again taking the best solution found as a reference and normalizing everything on the same scale. And the nice thing you see that on this variety of problems, Toolbar 2 upper bound is going down quickly and faster than any other of the solvers. We didn't choose specifically the problems that were the best for Toolbar 2. We take those that we could find at this time. And it's the same thing for the lower bound. The lower bound is not that bad. Actually, max HS is sometimes a bit better, but in the end, so it really, yeah, there is this connection with LP, and so yeah, we can prove that it's better than simulated annealing on CP on design. Also compared to a quantum computer, the local search algorithm, and This is it, Simon. I will be able to relax now. I give you, yeah, I stop sharing and I give you the screen.
Okay, thanks. Thanks a lot. So I put a link on the chat because we mentioned the solver toolbar too. So what is it? Is the solver we developed at INRAE for the cost function network. And I share my screen. So, is it okay? Do you have the screen? So yes. So I will continue the presentation by taking combinatorial problems for a practical exercise with toolbar 2 using the virtual machine that some of you may have successfully installed. For the others, it will be more like a demo how to use the solver. And for that, we will use Python. So on the website of Toolbar 2, you can find some documentation about the solver. And Thomas presented the various formats that he is able to read. And you can also find tutorials. So for different problems, how we can model it as a cost function network. You can also download the solver, but sorry for now, the binaries link are broken, so it will be fixed in the week. You only have access to the GitHub repository. This is an open source solver. Okay, so among the tutorials, I will present two problems. One is about a scheduling problem, so the airplane landing problem, and the other one is about clustering, the block modeling problem. Alors, so for that, you have to go to the virtual machine for those who can, and then open a shell, and we go to my first problem. So this scheduling problem is about airplanes. It's for air traffic controller at the airport to decide the sequence of planes, arrival time for the planes, and which runway for each plane arriving. So let's see inside this repository, so Erland. You have a publication by Bisley, so it was in transportation system in the 2002, I think, 2000, presenting the problem. And as I said, the question is to find a sequence for the airplanes, and you have as a mandatory constraint that two airplanes cannot arrive at the same time on the same runway, and also that you need a separation time between two successive airplanes on the same runway. Then the objective function is that you would like to for each airplane, you have a target time, arrival time, but it's possible to arrive a bit earlier or a bit later, but it has a cost. And you see the cost is a nonlinear function. It's just here given by these two lines. And this is what cost function networks are nice, is the ability to represent a nonlinear cost functions. So yes, for two airplanes, let's say this one and this one, you have a time window, so the earliest arrival time and the latest arrival time. And they should not overlap, and even more, there should be a separation time between any two planes. So let's see the program. So I close this. So I invite you to open Visual Studio. Okay. Open twice. Okay, so not the Sudoku, open folder. And then Erlang. So the practical exercise will follow some guidelines. And this is here in the README. And with Visual Studio, you can visualize, if you click on top right, to see this markdown okay, README file. So we will follow the steps. Here there are 10 steps. And the first one is to, on the terminal, to open the directory Erlang and to try to look at the data using this GNU plot command. So I will copy it. And okay, I will go to my, I'll make some, okay, and this one, okay, good. So for one of the data file, and in the Visual paper, we have 8 programs, 8 instances. You can see here the different for 10 airplanes. For each one, the time window for the earliest arrival time and the latest time. And the cross means the target time. So ideally, you should land the airplane at 1 at this time, and you will pay a cost if it is before or after. And the same for the other. So as you can see, it's not possible to land all the airplanes at the same time. Time is given here on the x-axis. It is, I assume, discretized in seconds. And here you have the 10 planes. We can have a look to other data sets like this one, which contains 20 planes, Erlang 5, for instance. Okay. So now I come back to my Visual Studio code, and I will open the Python script Erlang Py that you will have to modify. Okay, so this script is a working script. You can try it on some instance. So let's say here I can do this. So I will run Erlang Py with a very small data set. and get a solution. So this very small data set has only 3 airplanes. Okay, like this with overlapping time windows. And here you see the times that have been chosen. But there is something wrong, is that the cost of the solution does not take into account a different slope for the to arrive before instead of arriving after the target time. So the first thing that is asked in step 2 is to modify ANITI to be able to have this objective function with different cost if it runs before than after. So let's see the code. So the beginning is only some reading stuff to get the instance data. So it will contain in the AT table, you will have the time window on the target. Yes, yeah. Maybe enlarge my screen, possible. Okay. Yes. The PC corresponds to the cost. So it's a unique cost if you arrive per unit of time before the target time. And a cost for if you arrive after the target time. On ST is the separation time between any 2 planes. So what is the cost function network model? So first, we declare that we create a cost function network with an initial upper bound, let's say a large number. So here we give a big number. A few options are selected. And then for the, we create the variables. So for each airplane, we will create for each airplane, I will have a variable with a domain, which is the range between the earliest landing time and the latest landing time. Down here. Then, for the objective function, here is it. It's divided into a set of unary cost functions. That is, for each airplane, I have a cost function. So the 2 parameters for add function, the first parameter here, it says on which variables. So here I'm giving the index of the variable. So I assume the index is going from 0 to n-1. N is the number of airplanes. On the table of costs. So here it's Thomas said that we are manipulating tensors or tables for the cost. Indeed, we manipulate in the Python version only flattened vectors. Okay, so all the tensors have been flattened. And for only one variable, it's the same. And it's just a list of costs for all the domain values. So you do this iterator on all the domain values for the airplane, I. And the cost, here is it. So here you see the absolute function. So we it gives you the distance to the target landing time, which is here. And here it is multiplied by the cost associated to arriving earlier. So the first thing is to change this. So to take into account PCI 0 and PCI 1 if it is landing time is after target. So I let you modify the code. So here's the solution for this first question. I would like to have a different cost if my arrival time for the airplane, T, is before the target time. Which is here. So this is the target time. And else, if it is after, the cost will be PCI 1. Okay. So by doing just this modification, now it should be okay with the exact objective function. So I save this and go back to my shell terminal. And okay. So I have the solution. You see it is different now. The time arrival, it's they are short, smaller. And what would be nice, so it is for my question number 4, is to change the domain values so that we are we don't have domain values from the beginning of the time window to the end of the time window, but relative that the times the domain values are relative to the target landing time. So I just want to shift my domain values. So to do that, I can just modify here my range of domain values by shifting them from the target landing time. So I'll do this and this. Okay, -1. Okay, so let's save again. Maybe I can zoom in a bit so that it's larger for you. Okay. Okay, so if I do it again, oops. Okay. So here you see that the landing time now are relative to the target time, and if I want to check the objective value is correct, I can have a look to my input data. The cost here are before and after cost for airplane 1 to 3. So if I do minus 13 times the cost of minus 10, so I made an error here. So it means I arrive 13 seconds before the target time. And this is, as you see, because there is a minus 10, it means in this scenario, we are happy to land before the target time. And then 15 times minus 40, and then 3 times minus 20. We should get the objective value of minus 640. Okay. Okay, good. So now come back to the question, the next question. I have to squeeze my little bit. Oops, okay. So now we can try to solve a bit larger instance. So the airland 1, to see which optimum it has. Okay. So the optimum is 700 here. And the question is it the only optimal solution? So how to answer this question? So for that, you will have to tell to the solver, I want to know all the solutions. And there is an option for that. I remove the comment here, and I say I want all the solutions, at most 1,000 solutions. Okay, so if I do that, I don't get exactly what I want, because it will give you not all the optimal solutions, but indeed 1,000 solutions with different costs. So some of them are not optimal at all. So I have to change the initial upper bound. So Thomas said for constraint networks, we want solutions with a cost smaller than the upper bound, K. So we will give the initial upper bound, not 700, but 701, so that we have all the optimal solutions. Okay, so I do again. And here you can see there are two solutions, two optimal solutions of cost 700. And you see that the difference here is on the airplanes 5, 6, and 7 landing times. Okay. So let's go to the next question. If we want to solve a more difficult problem, so let's say airline 5, so I have to give back my original large upper bound. Okay, and again, I just want only one optimal solution. So I remove the all solutions option. Okay, I save again. And try to solve R15. Okay, so it takes a bit of time to create the model. And then we should see the first solutions. And the question here is the following. Use the virtual R consistency algorithms to improve performances. So VAC algorithm that Thomas briefly mentioned. So here you see some solutions that have been found. And I let the solver run and add an option to the constructor of the CFN object to say I want to do the VAC algorithm, but only in preprocessing. So this algorithm can be costly to achieve, to apply at every search tree of the every search node of the search. So we can do it only at the root if it is 1, or if I give a larger number like 10 here, for instance, it will be applied up to search depth 10. Okay, here I'm using 1 only. Okay, I save the thing. Okay, so it is still unfinished for this. Okay, so I will just stop it. So to stop the Python script, you need to do Control-Z, and then you have to kill the process. Okay, by doing kill %1. Good. So now I can rerun with the VAC algorithm. Okay, we let the solver run and go to the next question. Yes, in some cases, 2 airplanes have time window that are completely different, and they do not overlap. There will be always a separation time, sufficient separation time between these two for these 2 airplanes. So let's see, for instance, the case of airline 6. Okay. So for my instance 5, I should stop it. I will solve it later when I improve again. I'm just sure with the, so for instance here, yes, if I look at airline 6, you see that, for instance, the airplane number 1 or 2 or 3, they have no possible intersection with the last airplanes. So it means you don't need to create a cost function between these 2 airplanes to avoid overlapping. So it means there are some useless cost functions that have been created here. So the question is how to fix it. So which condition is required so that this constraint between the two airplanes is useful. So for that, I should mention this constraint a bit more. So as you can see, it's a binary cost function. You have two indexes here, so for two airplanes. And then you have a vector of cost corresponding. So okay, I'm trying to get more space. Corresponding to the domains. So I will iterate on the domains of the two variables, the last variable at the end. So variable I and variable j. These are the domains. And here is the cost. Yes, here. If airplane I plus the separation time between I and j is smaller than the landing time of the second airplane, or the inverse situation, that airplane j plus the separation time between j and I is smaller than the landing time of the first airplane, then it is fine. There is the situation is okay. So it has a cost of 0. Else, it has an infinite cost. So a forbidden cost, which is my initial upper bound top. Okay. So now, if I want to add the condition, I will do. Okay. If I will check that this condition can be false. Okay. But for that, here I want to make sure that it will arrive in some situation. So I will use the bounds of the domain of the variables. So if the latest landing time of airplane I plus the separation time is less than the earliest landing time of the second airplane, and the earliest is 0. Okay. Or the reverse case. So ATG okay. So if those situations are occurs, never occurs, then the cost function is needed. So I have to, oops, I have to put a note before that. Oops. Okay. Okay, so this is the modification to be done in order to not generate the binary cost function if it is not useful. So let's try now on the solver. Oops, maybe there is something. Okay, I will do the other way to be sure. There's no issue with Python formulation. Check. Okay, good. Okay, I save again. Okay, so here is the optimum for LN6. And of course, it would be useful to measure the solving time before and after doing the modification. Okay, so let's come back to the README. So now what we would like to do is to manage also the possibility to arrive for different runways. So for each airplane, we have to select on which runway and then which landing time. And for that, let's have a look to the second Python script, erlang2.py. Okay. This is it. And now I'm doing the modifications again that I have done in the previous file. So we just copy this. And again. Good. And also the modification of the ULRI cost. Okay, good. So for this new Python script, we have one more parameter for the command, which is the number of runways. Okay. And then I will have extra variables R here for each airplane. The main variable of size k to select on which runway for this airplane. The objective function is the same as before. And now for the non-overlapping constraint between two airplanes, we have an extra condition. If the two airplanes are on a different runway, there is no problem, no overlap, so it will have a cost of 0. Else, we have to look to the landing times. And you see that this cost function is not a binary cost function. It involves 4 variables. The two decision variable about which runway for airplane I and J, and the landing time of I and J. So you imagine that this table here, if you look at the end, you see that you will have to create a vector of cost for the Cartesian product of the domains of the 4 variables, and in the same order as inside the first parameter, so the R and then the T for I and J. Okay. So if I run this example on my very small problem, yes, it asks for this extra parameter. So how many runways? So let's say 3. And you see that even for this very small problem with 3 airplanes, it is quite slow. So the problem is that to generate the model, it takes time. And the tables of RET4 are quite big. And within Python, it takes time to do. So here, but it works for this small example, and we could have a solution in 30 seconds. So what is asked now is to improve the model by replacing the 4 RET cost functions by binary cost functions. And how to do that? The idea is to merge the domains of the time domain and the runway domain, the 2 variables corresponding to the time and the runway selection, into a single domain by doing the Cartesian product. So we will do this simple trick and see how it improves performance. Okay, so what I want to do is to forget about the 2 sets of variables. I have only one set. I call now X. And the range, I want to have a range from which is the Cartesian product of the two type of variables. So I will create a new domain. Okay, where I do the iteration over the runways and the landing times for the airplane. And the value, the corresponding value here, I can give a number that you can also give a name to the domain values. It means that for toolbar2, it's just a symbol. Each domain value can have a name, has a name. So for instance, this. Okay. So here is it. I will have, because I would like to have the time relative to the target time. I will do this. Okay, good. So now I can remove. I don't use anymore those variables. Only the new merged variables. So it means I have to change the iterators to create the tables for the cost. So let's say for variable I now, I have to add this range. So that we have a vector of cost that has the same size as the domain size of I. Okay, just like that. And for this overlapping constraint, no, because I merged the variables representing the runway with the time, I can remove and have only two indexes for the two airplanes. And I just have to change. So here, because it is the vector should be the iterations for all the domain values of I and then all the domain values of J. So I have just one little thing to change here is to be sure that I will iterate the domain values in the right order. So here I do the for loop for the domain of I, and then the two for loops for the domain of J. Good. Is it all for that? Yes, it should be okay. Let's have a look. So now I can try again. And here it is much faster, and it is the same, fully the same optimum. So I just reformulate the problem using binary cost functions only, and merging the domain variables. Why it is faster? It's because the tables, they are not very small, much smaller, but it's more effective in Toolbar 2 solver because it has native propagation on the local consistency and everything for binary cost functions, but also for ternary cost functions, but not for RET cost functions. So that's why you can see a difference of performance here. So let's try on a larger instance. So what we would like to know, if I have two runways, is it possible to have a better, to reduce the objective cost? And this is what I do here. I'm trying, so we know that the optimum of Airland 1 is 700, but with only one airport, one runway on the airport. If I have two runways, it is now 80. Okay. Last thing to speed up would be to add some symmetry breaking in order to help the solver with these runways. But I will skip this part. what you can check is, if I come back to my folder,
Simon,
oui.
Il nous reste plus que 45 minutes à peu près.
Yes. Okay. You can check on the paper, original paper, that the optimum value are correct. And see for Erlang 1, you get, we have the correct optimum for the case of 1 and 2 that I just tried with 2. So with 2 runways, it's 18. And indeed, if we continue this practical exercise until the end, we will see that we are able to solve for all the instances except on the largest one if we have many runways. In that case, we need a lot of memory. So what I would like to, before ending this part, returning to Thomas, is to show how it can compare to other approaches. So one is using integer linear programming. And for that, so I'm just closing this and this. And this, coming back. Good. So you can try on Erlang 1 using this command in order to create the basic integer linear model that has been proposed in the paper. So let's do it. Okay. And then solve it using the skip solver, which is among the best integer linear programming solver after Cplex and Givry. But skip is an open source solver, so it's totally free. Oops. So here I ask to find the optimum for the Erlang 1, and you see again it's able to find the same value in about the same time as toolbar 2 here for this example. Okay, so I invite you later to try for different instances, and it's possible to give a different number of runways. And just to show, because yesterday you had a constraint programming presentation, so using Minizinc, and for that you can click on the Minizinc interface and load not the block model, but the Erlang model. Okay, so you have two models for the mono runway or the multi runways. So in this case, for the mono runway, I can, before running the skip solver, I need to generate not the skip, but the Minizinc solver. I need to generate the corresponding input data for Minizinc. So using this command. Okay, good. So with the Minizinc, you have a formulation where you can find the same constraints that within toolbar. So this is for the non-overlapping constraint. here. But to express the objective function, you need to introduce extra variables in order to compute the earliness or tardiness time in order to be able to have at the end to express the objective, this nonlinear objective function. Okay. So now let's run it. Okay. So as you see, G-code was quite good here for this instance, able to find the same optimum in in less than 1 second. So the constant programming here is quite fast for the smallest instances, but if you try on larger instances, then you can see the difference, and the toolbar 2 on the skip solvers are better results, time results are faster for this problem. Okay, so thanks for following this part on the air landing problem. And in order to end this talk for this part, I want to show, yes, you can find the solution for this problem on the cost function library. So I will put on the chat this link. And here, if you follow and you go, so it's a repository of many cost function problems, combinatorial problems expressed as a cost function network. And you have in the crafted subdirectory, you have Erlang. And here you can find the scripts with the solution for the Erlang Python code for this practical exercise. Okay, so you have it here. I will not have time to present my second example on the clustering problem, but it is available, so you have it. If you go to the block model, you will find the corresponding paper. It was best paper at last CP. And you will have the instances, the Python model, and the README file, yes, to follow if you want to train on this problem. And then you can get the solution and the cost function library for the block model. Okay, so that's all for me, and I'll let Thomas continue the talk and more learning stuff. Maybe I can stop the sharing.
Thank you, Simon. I don't know if Thomas is here or no. He's muted for now. In the meantime, if there are any questions, feel free to ask.
Yes.
Yep.
So, do not hesitate if you have questions later to send me an email so I can answer.
Do you hear me?
Yes.
Yes. So if you have survived the previous talks by I and then Simon, and you're still there, we've kept the most exciting part from the end. And in this final part, we will show how we can actually connect CP with data. So previously we saw how we could connect CP with a deep learning layer just by feeding the output of a deep learning layer as tables for the cost function network solver. It's direct, it's easy, but yes, you still have to know the rules of the Sudoku game to do this. Then in plenty of discrete optimization problems, there may be data that gives you information about good solutions, what are good solutions. And you would like to exploit them to sort of build a criteria that is not a criteria that it can write directly, but a criteria that is defined by some data given by good historical solutions, for example. And thanks to the connection between cost function network and the Markov random field, these probabilistic models, it's actually feasible to learn the cost function network from data. And you can use them in your flow, combining constraints, the criteria of cost functions, and learn criteria also. So what does it mean exactly to learn a cost function network? Well, essentially, imagine that you have your decision variable or the observed variables, which are well identified. So for example, if you want to learn the rules of the Sudoku, these variables are the 81 cells of the Sudoku, and you will be able to observe them either directly from the SATnet dataset, for example, or either indirectly by taking pictures of Sudoku grids solved by people on their journal. And this gives you a set of assignment, and you assume that this set of assignment is it comes, so they are independent and identically distributed, extracted from an unknown distribution of what you know is just that they are working. They are high quality solutions. They are not bad solutions. They are good solutions. And the learning problem is actually to try to find a pairwise cost function network model that can be solved and to produce the same high quality solutions as, or similar, same as high quality solution as those you have observed in your assignment. So for the Sudoku, the idea is to use a set of solutions of Sudoku grids to feed them into a learning tool, and the output of it should be ideally, it would be the CFN model we wrote in Python, but it will not be exactly this. It will be a cost function network which have the property that if we solve it, we get a reasonably good solution for the Sudoku. And this can be done because we have this connection between Markov random field and cost function network. We know that a minus log x transform and exponential minus x transform allows to take a Markov random field and transform it to an associated cost function network, which I denote as ML, L for the log, reminding us that we apply a minus log transform. And this connection, so it's useful because essentially it allows to define a probability distribution. We have a sample of solutions, a historical solution, and it will allow us to use a very old and a very fundamental way of learning, which is maximum likelihood principle. It's a principle that has very strong and nice asymptotic properties. It is consistent. So you know that if you have a very large sample, you will learn the correct stuff. It's an asymptotic property only. And then essentially what you want to do is to find a cost function network such that the associated Markov random field gives maximum probability to the assignment you observe. And this can be interpreted in the domains of costs or energies. Actually, Yann Lequin gave a recent talk at AAAI 20 showing this also. If you want to maximize the probability of your dataset, because the elements are independent and identically distributed, by independent is the crucial property, you are allowed to take the product of all the probabilities. And because some are easier to deal with, we take the log to go to ML, and the log likelihood is a logarithm of the probability of observing your data. And this can be written by, so you do simple maths essentially, and it flows easily. You have the normalization constant that appears somehow at some point for which is Sharpie compute to compute, but it's okay. We will deal with that later. You can realize that if you maximize the likelihood, the log likelihood, what you are doing in the cost domain, so in the CFN, is that you are giving a low cost. So you try to minimize the costs that will be given to the samples you observe. It's logical because you know that they come from a high quality set of high quality solution. And at the same time, you will try to maximize, because of the minus, this is the soft minimum of the cost of all the possible assignment. So in some sense, you are trying to push the solution you observe towards zero, the costs, and at the same time pushing smoothly, because of the soft minimum, pushing the costs of all other solutions or all solutions towards greater value, so maximizing them. And the difference here, you try to increase the contrast between solutions and you observed and the rest of the assignment. And so this works well, and essentially what we mean by learning a CFN, what does it mean exactly? Actually, we restrict our language. So we will not be interested in any cost function network, but only on pairwise function network. So cost function network where there may be a function that involve at most 2 variables. Of course, if you have n variables, there are at most n minus 1 divided by 2 of these functions. On the Sudoku, this means at most there can be 3,240 functions. And each function is defined by these tables. You remember 9 by 9 tables, so 81 numbers, which we will have to learn for each function. So there is a total of 300,000 roughly parameters to learn. All the function on the pairwise function and all the elements in the size of the tables need to be decided which values they will take. And because we will use convex optimization to solve this, we assume actually that the costs are real for a moment, and we use floating points to learn these costs, and then as usual we will transform them into decimal costs that Toolbar 2 can handle. Of course, it's a bit frightening because it can lead to a very dense problem with many functions and matrices associated with each. So ideally, what we hope, and we will see that it's feasible to reach this hope, is that plenty of these parameters will be equal to 0. And if plenty of these parameters are equal to 0, then the associated functions are useless and we can forget them. So the algorithm we will use, it will optimize all those tables simultaneously, but it will also set many of these tables to 0. And for those tables that are equal to 0, we can forget the function, we remove it. So in some sense, the algorithm, it simultaneously learns where there are functions that exist, and for those that exist, it decides the costs which are associated with them. And to try to go in this direction of having 0 cost when it's useless, we use a very usual trick in machine learning, not a trick, a very usual technique, I would say, to try to bias, actually. We just penalize the likelihood. So you take the log likelihood and you penalize it by the norm of the cost you are learning. So the bigger the cost you learn, the higher the norm will be, and the more you will penalize your log likelihood. You try to maximize it, so you're not happy to penalize it, and you will prefer to put a 0 here than to improve the log likelihood in some cases when the parameters is not crucial. And the norm you use here is important to get many 0. It's very well known in machine learning, and the L1 norm especially, or the L1, L2 norms, the group lasso and the lasso norms, as they are called also, are very useful here. And so to solve these problems, there are plenty of techniques available. I don't want to go through all of them, but there are expensive Monte Carlo methods that really try to solve this normalization, constant evaluation, pseudo log likelihoods, which have some weaknesses, approximate log likelihoods, which approximate this normalization constant, and which are very nice, and we will use this one because they can accept probabilistic input. essentially you can learn a CFN not from exact solution of the Sudoku, but from indirect observation of the solution, for example, from images of the solutions. And to solve this approximate log likelihood optimization, the function you have to optimize is convex, so you can use convex optimization solver. And the L1 norm is not differentiable at the origin, so you are restricted in your choice of algorithm. And we use a recent proposal by Park and colleague. The colleague among them is Stephen Boyd, famous convex optimizer. It uses this family of approach which accept probabilistic input, and the algorithm is alternating direction multiplier method, which is very nice convex optimization algorithm. We discovered it at this occasion, and it's very easy to add norms. So the code we use, we have extended it to use also the L2 norms, for example, the L2 norm. And it has also extra property. It can learn hybrid problems with both discrete variable and continuous variable, which may be useful if you have data which is equipped with what we call contextual data, which is known when you solve the problem, but is also available in each sample. And the only thing with this problem, this algorithm, is that you need to set this penalty multiplier lambda, which is here. You have to choose the right number, because otherwise you may overfit the data and produce very dense model with random function inside. If you put it too high, you learn a problem which is empty. And so how we do, we take our data. In our case, will be images, in the most complex case, images of Sudoku grids. We go through the net, for example, but it can be another situation, of course, and we get training sets and validation sets, but which are probabilistic information, not exact information. We feed this into the convex optimization algorithm with a value of lambda, which initial value of lambda, we will do grid search. It's a one-dimensional optimization problem. We get a cost function network. We take a solution from the validation set, which is only probabilistically known in the worst case, and we feed it inside toolbar 2 as we did before with the visual Sudoku problem. We apply toolbar 2 with this partial solution, and we get a solution. And the solution, we again feed it to the validation, to the supposedly probabilistically known solution to see if is it likely in terms of probability that the solutions that toolbar 2 produce, does it resemble probabilistically the exact, or well, the probabilistic information we have in the validation set. And essentially we repeat this loop, changing lambda and trying to find solutions which are close to the validation set. Then we can go through a step which we call empirical hardening to create constraints, which is very simple. And then you have a CFN at the end with both the criteria and the constraints, and you can have your knowledge. If you have some extra knowledge to add, you can add it at the end and solve it with it toolbar 2. So this problem of tuning lambda is difficult, and what we do is we do empirical risk minimization, as I said. So for each solution in the validation set, we assign only a fraction of it, as in the int of the Sudoku, and we prefer lambdas that give solutions which are close to the full V, which is known in the validation set. And close to is different depending on if you have exact solution, then we use simply a mean distance between the solution that toolbar 2 found and the expected one. And if we have probabilistic information that the net produce, for example, we simply prefer lambdas that give solutions which have high probability according to the net output. So it's very easy to set this lambda. And if you cannot do this, you can use a heuristic machine learning solution. For example, there is an algorithm which is called stars that can be used. And this parameter lambda is very important. We use the L1 norm. If you put lambda too low, you will get a lot of noisy function in your cost function network. It's very hard to solve without the D here. If you choose the optimal lambda, you will have a good number of functions, less noise, plenty of zero cost, plenty of missing functions. And if you put a too high lambda, as I said, then your CFN ultimately will be empty and everything will be an optimal solution. So it's useless. And in this loop, you have to solve optimization problem and p-complete optimization problem, but you can control the effort you spend there, either by bounding explicitly the optimization effort by the number of backtracks, for example, or also by controlling the amount of value from the validation set solution you assign. If you assign only a small fraction, then toolbar 2 has a lot of extra job to do to complete it, to optimize out. If you assign more of them, that obviously the problem becomes exponentially easier, and this is easy to control the complexity of this loop, therefore. And this empirical hardening is easy. Simply, if you have costs at the end that you observe which are never violated in the training and validation set, you can set them to infinity or to k, and then they become constraints. And applied to the Sudoku, we use the test set that comes from a neural net paper, this recurrent relational net paper. They have a very nice data set with very hard Sudoku when you have only 17 ints. They are so-called minimal Sudokus, and more dense Sudokus with more ints, but still less than SATNet. And you can see that with 2000 problems, you start to be able to solve. So this is the correct, the number of solved grids. You start to be able to solve grids and find the right solution. And for the easiest problem, around 6,000 samples are enough to solve them. And it's far better than this relational recurrent relational nets, which needs more samples to get only an approximate solution. Here we get exact solution always at 13,000 samples. RRN needs 180,000 samples and does not reach the same number of optimal or exact solution. And this gives you an idea of how the running time of toolbar 2 when it tries to solve Sudoku using learn CFN. When you don't have enough sample, you learn noise essentially, and problems are very hard. And they have plenty of functions, as I said. When the sample size is very high, when you have 12,000 samples, for example, the problems are very well learned. The solving time is very small, the order of the same with hard constraint and milliseconds, let's say, and you get the exact solution almost always. And let's do this on the Sudoku using the virtual machine. So you can look into the code, but I just want to show you what we have. So we have the SATNet dataset. We have these minimal problems for the recurrent relational net papers with solutions which are problems which are challenging for humans, really. If you try to solve them, you will see. With only 17 hits, it becomes very, very, very nasty Sudokus. And I pre-computed the lambdas by doing grid search. And we have the output of LeNet as usual. We have this PMRF algorithm, which is coded in Python, thanks to Céline Brouard for working with us on this. And we have two versions of the Python program, one that runs on exact data and one that runs on the output of LeNet. And let's see how it works, for example, so Python 3, I will try this, the exact output. I will use 8,000 samples, and I will try to apply the resulting CFN to SATNet instances. It's learned on the RRN training set using only 8,000 samples. You have the sufficient statistics which have been pre-computed also. So this is the convex optimization algorithm that runs. It's an iterative algorithm, and remember it has 300,000 parameters to optimize, continuous parameter to optimize. So it's not a simple problem, it's a cubic algorithm. It takes time. It's obviously difficult to apply this on very large when the number of variables is very large, but it's programmed in NumPy, and so it's a very basic implementation. We don't use any fancy stuff, no GPU, no things like that, which could be very useful in practice. And well, on my laptop, it runs much faster than this computer because this is a virtual machine that runs on AMD machines with an old CPU. And so it's not very fast. It's much faster on my laptop. It will take something like 50 iterations, I think, to converge. So So yes, the lambda, as I said, is pre-computed. I optimize it using grid search, using the RRN validation set. And so it solved it. And so it says, okay, primal and dual of the convex optimization have met after 47 iterations. The CFN learn has 813 binary functions. So in the Sudoku, in the usual model of the Sudoku, the one we wrote in the first example, if you count the number of functions that you have added inside all those click, at the end it generates 810 functions. So we know that here we have learned too many functions. So the model is not exact. For sure, it's not the exact model of Sudoku. But if we apply them and ask Toolbar 2 to solve a very numerical problem, imagine the problem. We have a problem where every function is a pairwise table of floating cost numbers which have been rounded to their nearest decimal number with 6 digits after the decimal point. So it's a fully numerical problem with plenty and plenty of numbers, but yet Toolbar 2 is fine with it. You see it solves them very quickly. Actually, when it's green, it says that it has found the exact solution. And actually on the SATnet dataset, the SATnet problems are very easy. And if we go to the bottom, it's still solving, but it will finish quickly. It solves, we'll see, yeah, it solves all problems exactly, no incorrect solutions. The convex optimization took 70 seconds. The average time for Toolbar 2 to solve a problem is 1.4 milliseconds, so it's very fast. And yeah, it works. It can handle this data, and the L1 norm is crucial here, really. If we shift to the much harder problem from the recurrent relational net paper, those minimal problems, you will see that it behaves. This test on SATnet could make you think that, okay, we have learned the exact Sudoku models, it's great, it's direct, it works. Let's try. Well, it's a pity that the model has to be retrained. I didn't save it. I should have written it. So we'll have to go to the 47 iterations again. But essentially what you will see in a few, in 1 minute, I say probably, is that Toolbar 2 will still be able to solve the problems. Actually, Toolbar 2 runs in a bounded backtrack mode. So it will never do more than 50,000 backtrack. And see if it doesn't solve after 50,000 backtrack, it just stops. And because the problems are harder, in some cases this will happen and you will get no solution. In some other cases, it will find a solution which is a wrong solution, which violates difference constraint because it has not learned actually hard difference constraints. We didn't do this empirical hardening here. It learns soft difference constraints, and some of them are imperfect. Actually, some of them are redundant probably or useless because we have 3 extra functions. And so you will see that it's very important when you compare machine learned solvers for logical tasks, it's very important to compare them on the same hard solutions or not. So you see it's still able to solve those difficult problems. It produces exact solution many times, but it takes much more time. And I think that, no, it's still okay. Everything is still fine. At some points, it will not be able, yeah, here it is. It couldn't solve the solution in the 50,000 backtracks time. And so it spits bullshit, nonsense, and it does not solve the problem. And this is how it goes. You thought, one could think on the SATnet that it was a perfect solver. It's not a perfect solver. And of course, you can do the same thing with the visual Sudoku. The visual Sudoku, it's different because we used images as solutions. They go through the net, you go this probabilistic output, you use it to learn, and you also use it to give the hints to Toolbar 2. So it's a very complex, in this case, the model that Toolbar 2 solves is very complex because it has the numerical information from the net that comes from the convex optimization module, and it has also the numerical information that comes from LeNet. It combines them together and it tries to solve them. And you will see that the convex optimization algorithm has more difficulty to optimize here. So the lambda is different from the previous one. It was optimized again by grid search. It's different because the data is different. It's the same the set that has been used, but it goes through LeNet, and LeNet gives this probabilistic output, which is an imperfect representation of the grids that were initially known in the RRN paper. And so, yeah, the matrix of sufficient statistics that is needed by the convex optimization algorithm is not the same, and convergence will be slower. I think it requires something like 66 or 67 iterations, so we'll have to wait a bit. And then we will see that with 8,000 samples, it's still able, even if we play with images, it's still able to find solutions in a vast majority of cases, exactly as the exact solver previously. It will, of course, make errors in some cases because the ints will be wrongly decoded by LeNet, and so you will solve a grid where the input is not optimal, but as in the exact case previously, it will be able to correct the errors of LeNet in many cases, and it will be able to produce exact solution even when LeNet makes error. And this is the power of exact optimization, which is available here, because we are strongly optimizing the objective. We are, so you see, let's cool down this stuff. It's still solving. So in many cases, you see that. Let's find an example here. Well, it has corrected one error of LeNet here, but not both, so it made some mistake. But in many cases, you find the exact solution. And in some cases, yes, LeNet made 2 errors here, but the toolbar 2 corrects them. And so we get at the end, well, I won't let it run because it's a bit slower, you'll see also, because it's more difficult. But roughly at the end, we will get, I will stop it, we will get a better performance than the theoretical optimal performance given the error of LeNet, because we are able to correct the error of LeNet, even if we are using a probabilistic input from images to learn the data. And actually, I just want to finish by showing you what we learned. So I stored here the output of the convex optimization algorithm. So this is the output of the optimization, the convex optimization, using 13,000 samples and this value of lambda and the L1 norm. And let's look what it is. It's a CFN network. So the nice thing, what we learn, we can look into it, we can understand it, we can see what it does. So it's produced by a DMM. We have all those variables that have 9 values in their domains. It's expected. We have 81 of them from 0 to 80s. And the functions, let's look into the pairwise functions. The functions that involve x0, for example. I will look on the function that involve x0. So I have found one here. And the pairwise, you can see that we have a small positive cost here because it's the first time of the identity matrix and it's different from 0. But otherwise, it's exactly equal to 0. And the next term on the diagonal is again different from 0. So we are discovering this sort of scaled identity matrix, which represents the difference, but it's scaled by a small number. It's not important. It will be big numbers actually inside toolbar 2. We have a 9,847 here, and we have 8,490. And it's exactly a different constraint with which is learned. It's very funny to see this. We have the exact, and then if we look to the scopes, let's look to the scopes. So we discovered that there is a constraint between variable 0, the first cell of the Sudoku, and 1, which is the next one, and 2, okay, and 3, which, okay, it is on the same line, 4 on the same line, 5 on the same line, 6, 7, 8 on the same line, 9, next line, but same column, same subcell again, and then we shift to 18, which is the exact expected things we would hope, this is the next variable in the first column. So we effectively skip all the variables for which we know there is no interaction in the definition of the true problem. And so it exactly learns, except that it has when we have a little sample, it has 3 extra functions, but with 13,000 samples, what we can observe, it's purely empirical, we have no proof of this, of course, is that it exactly learns the correct formulation of the Sudoku. And this is it for the virtual machine. And let's finish on this stuff with sort of conclusion. So yeah, it's the maximum accuracy that was expected was 74 because of the accuracy of LeNet in the visual Sudoku case. But actually, Toolbar2 is able to correct this LeNet error. It reaches something like 78% accuracy because it's able to correct some of these mistakes of LeNet. So if Simon did not cover it, we had no time, we underestimated the time we needed. We applied this on more stuff than just Sudokus. We also applied it to Renault problem of learning user preferences on a Renault dataset, thanks to Hélène Fargier, which compiles dataset from Renault. And the paper, the CP 2020 paper that describes this is in the directory and the VM if you want to look at it. And this is the final conclusion for this tutorial. Yeah, first about CFN and WCSP solving. We have really made huge progress in the last decades. We have those fast approximate LP bounds. They are much tighter. You should realize this. They are much tighter than the bound you can get from constraint optimization solvers like Minizinc or other solvers that use bound arc consistency on the sum constraints to sort of optimize those problems. They are fast, they are connected to LP bounds, and they subsume arc consistency in the art case. So they have very nice properties. The Toolbar2 does just this filtering that is based on cost, not only on constraints. And the algorithm can be made aware of the structure of the graph. They are guided by cost because cost offers for free value ordering heuristics. And the HBFS algorithm is nice because it produces this optimality gap exactly as Cplex and Gurobi provide. As you solve, you see the gap that reduces, and you can stop before the end if you want. The next important element is that, yes, this capacity to deal with very large integer cost, which is crucial because being able to tackle problems with very large integer cost, we are actually able, like ILP solver, to deal with fine-grained numerical information. And this is the crucial point that makes it possible to easily discuss or interfere with machine learning, with numerical machine learning, I would say, not with symbolic machine learning, but with numerical. So with deep learning, but also with other machine learning algorithm. It can be regression, it can be SVM output. Anything like this can be fed into Toolbar2 after proper rounding that Toolbar2 will do automatically. And we have these tractable learning algorithms, and this is connection with machine learning. It's still cubic, so yeah, it will not tackle problems with 10,000 of variables for sure, but it allows to connect with deep learning, both at the learning step and at the prediction step, and with the adjustable power of an exact solver. So you can bound the number of backtrack and decide when, how much time you are ready to give to the solver to solve these problems. And I think this is it. The final slide. What time is it? Yes, we are on time. So final slide. To also tell you that all this stuff is working quite fine. The progress has been good. But still, when we observe what Toolbar2 is, we know it very well, of course. We know that there are plenty of limitations inside Toolbar2. So yes, it's easier to learn now. It has this Python interface, which makes it easy to apply to a new problem. You can build your cost table with Python. You can build your cost table with NumPy. It can be efficient with NumPy. But still, yeah, there are global cost function inside, but the fact that propagation in cost function network is non-monotonic, you may have decreasing costs, makes everything more complex. And there is a lot of work still to do on this. So if you don't know how to spend your time, look into global cost function propagation. It uses the same graph algorithm to enforce, for example, FDAC or other algorithm. It could enforce VAC for the moment. Nobody try to enforce VAC on global cost function. It's something that is feasible for sure. And there is a lot of work to make things more incremental here. Also, we deal with interval variables and arithmetic filtering very poorly. There has been just one thesis on this. It was a very nice thesis by Matthias, but yeah, thesis is only 3 years. You cannot do a lot of stuff in 3 years. Also, you want to preserve efficiency when you deal with constraints. Currently, for example, the simple R consistency algorithm in toolbar 2, if you apply it to constraints, I said it is equivalent. It's equivalent, yes, but it's cubic instead of being quadratic in the domain size. And actually, there is a way to make it quadratic only. We published it, but it's not implemented. And if you go beyond R consistencies, there is a job to do and to publish, actually. This tight connection with LP is also important because we saw that the bounds we use are actually very tight. And with this universality link, you can take an LP, convert it into a CFN, and produce a bind for this LP using VAC. And VAC is a sort of generalization of max flow. You cannot realize it with our tutorial, but if you look into it, it's a generalization of max flow algorithm that uses augmenting DAG instead of augmenting pass. But in some sense, you have an algorithm which is less powerful than LP, but more powerful than max flow. And it produces nice bounds very fast, very efficiently. And you definitely have to dig this. Something that could be done also is to try to unify cost function network with constraint optimization problem. In constraint optimization problem, as you saw yesterday with Pierre, you have these cost variables that you can aggregate together in the sum constraints, for example. And actually, as I said, the bounds are poor. Just because you do bound consistency on the sum constraints, the bounds are poor. And CFN bounds are tighter. But you could take the best of both and have cost variables in cost function network, propagate them using cost function network algorithm, but yet make them available as variables. And this would give the CFN framework a very nice reflectivity in some sense, because you would have variables that would be able to speak of the value of the global function, exactly as in SAT, you have this ability to speak of the truth value of the formula with a single Boolean variable. And that would be great. And you could speak about also of multiple criteria, having multiple CFN with multiple cost variable. You can improve parallel search. You can try this to solve, well, Simon shows this on air landing problems, but you could try this for scheduling. And instead of minimizing this good old max span criteria, try to maximize average tardiness using improved bounds, doing energetic reasoning, for example, but extended to account for cost and not only for feasibility. And of course, the learning side is just very premature. We just did this stuff using this convex optimization algorithm. Maybe better algorithm that could improve the sample size you need, that could learn constraints directly, that could learn global constraints or global cost function, and also better integration of CFN with deep learning could be interesting, of course. So there are plenty of things to do. And I will stop here with 4 minutes beyond schedule. Sorry about this.
Yeah. About almost right on time.
Yep. So
if there are any questions, we can take them for a couple of minutes.
Are there still participants?
29.
Yeah. Okay. Some left, but some remains.
Otherwise, I want to thank you, Thomas and Simon, for your presentation today. And if there are no questions, I see Simon answered most of them already during your presentation, Thomas.
Yep, that's where the agreement between Simon and I would answer the question while he presents, and he would do the reciprocal service when I present. So he did his job. I did mine also. Maybe I will stop sharing my desktop. And
okay, well, if there are no more questions, we will close the session for today, and we will resume tomorrow at 11 Paris time with Chas Guns.
And you will see the visual Sudoku again.
I think there's a question.
Yes.
I don't understand the question.
Let me try to understand it. Available paper, probably. Yeah, well, I don't know which paper you refer to, Jovial, but the CP 2020 papers that shows that we can connect, use convex optimization plus deep learning to solve visual Sudoku. It's actually available in the VM, in the virtual machine. In the Sudoku CFN Learn directory, you have the PDF. Otherwise, you can find it easily on internet, just typing.
I put the link on the Q&A. Mm-hmm.
Okay. Well, actually, I turn off my camera. I could. And another question: can we do a reverse proper? We have non-solution instead. That's an interesting question. Really, yeah. If you look in the traditional way to learn CSP, which was the software like Conac and Quack and that Christian Bessière and colleagues developed, they actually use this Anguin learning frameworks where you are assumed to have an oracle that can answer both positive and negative queries. And here you would have negative queries. And yes, of course, it would be interesting. Why did we focus on the situation where we have only positive answer? Is because we think that it's a more frequent case in practice. Actually, the main motivation for doing this is protein design, again, because this is my main center of interest. And in protein design, what you can observe in the nature are only in working proteins. The proteins that don't work, the nature that does not keep them. They are not in, and I think it's actually true for many problems. The non-solutions, nobody is interested in them. So you have to imagine a situation where you have non-solutions. And the only situation I think where you have those is when you have an expert that would say, oh, this is bad. And then it's a different situation, yeah. It's not the big data situation that we are often faced with in these modern times, where data has been accumulated because it's interesting. And solutions are interesting, but non-solutions are not so interesting. For example, it's very difficult to find data sets of non-solution of the Sudoku problems. I think that there is no such data set. On the contrary, you can find zillions of data sets of Sudoku solutions. On Kaggle, there is two data sets with 1 million solutions of Sudoku. So yeah, I have no algorithms to exploit them, but for sure this would be interesting. The zebra problem, yeah, the smaller and smaller problems. Yes, of course, we can try to learn the zebra problems. It would be yeah, noisy data. Well, so the zebra, yeah, we haven't tried on it. We could try. You could try this. Noisy data, we deal with this noise. Huh? As I said, both the learning algorithm and the prediction algorithm accept probabilistic input. And here we don't do anything on this probabilistic input. So we don't calibrate the output of the net. It's very blunt. It's very stupid. It would improve things, and Thias will show this tomorrow. And this calibration would help both the learning and the decoding. But yeah, it's here just to show that even simple stuff can work. So yes, noisy data, we should do some preprocessing, but we didn't do any preprocessing. Okay, Nassim, go ahead. Maybe you should open your mic and say it loudly.
I guess for the zebra problem with only one solution, it's good to relax.
Yep.
Constraint.
Yep. But you can relax constraints and then produce good quality solutions that violate only one or two constraints at most, for example, and then produce all these. I need to have access. Okay. Then I don't know if we can open the access, but if it's not feasible, then just type the questions. For me, it's of course feasible. Probably a restriction of the webinar that the webinar version of Zoom does not allow to open mic to attendees. I don't know.
Yes, you have to raise your hand and then we can give you the mic.
So Nassim, raise your hand. It's in the, where can we hand? Yeah, I saw this. The raise hands somewhere.
Now you can talk.
I need to have
hello?
Hello, Nassim.
Can you hear me?
Yep.
Yeah, thank you for the amazing presentation. It was very interesting. I just have one last question. Since you showed that the CNF can take in the probabilistic output from a neural network, which is the value from the softmax in the case of LeNet.
Yep.
And I was thinking maybe because LeNet goes through a convolutional neural networks to produce a feature map of the input, right?
Yep. Yes.
I thought if it was possible to give the encoding that was generated from the convolutional neural network, from the convolutional part only, to the CFN part.
I must confess. Well, clearly, every tensor that is used inside the net, it's a tensor. So it represents numerical information organized in tables. And there is no reason why it should not be fed to toolbar 2. But then the question would be, what would you want to do with this? Which problem would you like to solve with this tensor information? The final layer, the output we get on the final layer.
For instance,
yes.
Yeah. Continue, please.
Yeah, the final tensor we get in the outputs is the log softmax. It's a log softmax output. It's minus log softmax output actually, but it has an easy probabilistic interpretation. It can really be interpreted as a minus log probability. For the more internal layers of the net, the more convolutional or even the pooled, all the layers inside, the probabilistic interpretation is probably not as straightforward. So I've not thought, I haven't thought about it yet, what you could do with this. I haven't, but in principle, of course, you can do it.
Okay. So in short, you could see it as a process of, it's a cost function acquisition process.
Yes, exactly.
This is what.
Yeah, in the simple case where you just want to analyze input from an image that defines an assignment of variable, it's very simple. If you want to really learn the cost function network for the moment, you have to use this convex optimization algorithm. There are few.
All right.
There are few proposals to learn graphical models using neural nets, but like these RRN papers, for example. But for the moment, it seems suboptimal, sub-efficient compared to convex optimization.
All right. Well, thank you a lot for the answers and for the presentation.
Thank you for attending, Nassim, and for asking the questions. And I think we can stop here and say bye-bye and to everybody. And if you want to play with the VM play on the Toolbar 2 website, go ahead. Everything is available and free. Bye-bye.
Right. Bye.
Okay, bye.
Salut Simon.
Merci beaucoup.
Au revoir Christian.
Je suis arrivé à la fin de votre exposé. C'était très bien, merci beaucoup.
De rien. Ouais, on a essayé de rattraper les... Bah, c'est bon, on s'en est sorti. C'est pas optimal,
Oui,
mais c'est toujours... Allez, à demain.
À demain.
Merci pour le job, Christian.
Louis, tu peux fermer la session?
Ouais. Moi, je vais me déconnecter.
Pardon, c'est toi qui es redevenu l'autre.
Bonne soirée.
Je suis
Ouais.
redevenu.
Quand tu es revenu.
Ah, ok. Good night, everybody. See you tomorrow at 11 with the talk of Thias Guns. Thank you. Bye-bye.